Hello and welcome to our journey through the invisible forces that govern our world. Tonight, we are not just talking about another theoretical physics scenario or astronomical phenomenon, but about humanity's greatest defense challenge, a cosmic encounter that could redefine everything we understand about survival itself. Something extraordinary was discovered in the depths of interstellar space on July 1st, 2025. A visitor that had travelled for millions of years through the void between stars, carrying with it mysteries that would challenge our understanding of what it means to defend our world against the unknown. This cosmic wanderer, designated 3I/Art-Lars, is not merely another comet or asteroid passing through our celestial neighborhood. Unlike the familiar objects we observe in our night sky, this interstellar traveler is a messenger from alien star systems, its composition and behavior revealing secrets that become terrifyingly clear only when we realize it might not be traveling alone. What makes 3I/ATALS humanity's ultimate defense challenge isn't just its extraordinary origin from beyond our solar system, but the unsettling reality that this ancient voyager carries with it an entire swarm of unknown entities, a cosmic armada that forces us to confront our complete unpreparedness for what lies beyond our protective bubble. Before we plunge deeper into this ultimate test of human ingenuity and survival, imagine where you are right now, sitting in a familiar world, protected by nothing more than distance and ignorance, perhaps unaware that something from the depths of space could be approaching with the power to challenge every defense we've ever conceived. If stories like this compel your imagination, consider subscribing or liking this program. It helps more curious minds connect and prepares us all to face the extraordinary challenges that the universe might one day place before humanity. Now, take a moment. Let your mind reach beyond the familiar boundaries of our solar system and prepare to understand what it truly means when humanity must defend itself against something truly alien. When 3I/Atlas reveals itself not as a simple cosmic visitor, but as a swarm that tests the very limits of our technological capabilities and collective resolve. This is the beginning of a story where human ingenuity collides with cosmic mystery across the vast emptiness of space, and we must confront the ultimate question: are we prepared to defend our world against visitors that operate by rules we've never imagined? The night sky above Chile's Atacama Desert held its usual blanket of stars when the Atlas telescope at Rio Hurtado began its automated sweep on July 1st, 2025. Each evening, this modest half-meter instrument performed the same methodical dance, photographing patches of darkness in search of moving objects that didn't belong. Most nights brought the familiar catalogue of known asteroids and distant galaxies. This night would be different. At coordinates, marking the border between constellations Serpens Cauda and Sagittarius, something faint caught the computer's attention. Object A11 Ply3Z appeared as little more than a smudge of light, registering magnitude 18, roughly 100,000 times too dim for human eyes to detect. Yet within hours, follow-up observations revealed this unremarkable speck was travelling at an extraordinary speed, 61 kilometers per second relative to our Sun. Dr. Maria Santos, the duty astronomer monitoring ATLAS data, streams from her office at the University of Hawaii, first noticed the anomaly during her morning coffee routine. Years of experience had taught her to recognize the subtle signatures that separate cosmic wheat from chaff. The velocity was immediately suspicious. She would later recall, nothing in our solar system moves that fast unless it's been gravitationally accelerated by something massive, or unless it came from somewhere else entirely. Within 24 hours, Telescopes across 3 continents turned their attention toward a 11 Pli 3Z. The Zwicky Transient Facility in California had already captured pre-discovery images dating back to June 14th. Atlas stations in Hawaii and South Africa added their observations to the growing dataset. Each measurement confirmed what the initial calculations suggested: this object was not bound by our sun's gravity. The mathematics told a remarkable story. 11 Plat 3Z followed what astronomers call a hyperbolic trajectory, an orbit so energetic that it would carry the object back into interstellar space, never to return. Its orbital eccentricity measured 6.1, meaning it possessed more than 6 times the velocity needed to escape our solar system permanently. Such extreme values could only result from one scenario. This visitor had arrived from the depths of space between the stars. By July 2nd, the object revealed another crucial characteristic. Unlike the rocky asteroid initially suspected, an 11 Pli 3Z displayed a faint but unmistakable coma, a fuzzy cloud of gas and dust streaming from its nucleus as solar heating began sublimating surface ice into vapor. The International Astronomical Union's Minor Planet Center faced a classification decision. This was clearly a comet, and clearly interstellar. Following established conventions, they designated it 3I/AT-LS, the third confirmed interstellar object to visit our solar system. The discovery placed 3I/AT-LS in exclusive company. Only 2 previous interstellar visitors had been definitively identified. In 2017, the Pan-STARRS telescope in Hawaii detected Oumuamua, a peculiar elongated object that showed no cometary activity despite its close approach to the Sun. 2 years later, amateur astronomer Gennady Borisov discovered the comet that bears his name, providing the first clear example of an active interstellar comet. Yet 3I/ATLAS brought unexpected characteristics that distinguished it from its predecessors. Spectroscopic analysis revealed an unusual chemical composition, with carbon dioxide emissions dominating over water vapor, a reversal of the typical pattern seen in solar system comets. This CO2-rich signature suggested formation in an environment colder than the regions where most of our local comets originated. The James Webb Space Telescope quickly added 3I/ATLAS to its observing schedule, employing its infrared capabilities to peer through the growing coma and analyze its molecular composition. The results painted a picture of alien chemistry, water, ice and vapor, carbon monoxide and carbonyl sulfide all present, but in proportions that marked this comet as definitively foreign to our cosmic neighbourhood. Dr. Alan Fitzsimmons of Queen's University Belfast, a veteran of interstellar object studies, emphasized the significance of these measurements. Every molecule we detect tells us about conditions in another star system billions of years ago. This comet formed around a different star, in a disk of material with different temperatures, pressures and chemical abundances than existed in our own solar nebula. As July progressed, 3I/AT-LS brightened steadily, approaching its closest point to the Sun, scheduled for late October. Unlike Earth-threatening asteroids that dominate planetary defense discussions, this visitor posed no collision risk. Its trajectory would carry it no closer than 1.8 astronomical units to Earth, roughly 270 million kilometers, safely beyond Mars's orbit at its closest approach. But 3I/AT-LS represented a different kind of significance. Its arrival marked the beginning of what astronomers expected would become routine: regular detection of interstellar objects as survey telescopes grew more sensitive and comprehensive. Current estimates suggest that several interstellar visitors enter the inner solar system each year, most too small and distant to detect with existing instruments. The Vera Rubin Observatory, scheduled for full operation in the coming years, promised to revolutionize interstellar object detection with its ability to survey the entire southern sky every few nights. Computer models predicted this facility alone might discover hundreds of interstellar objects annually, transforming these cosmic refugees from curiosities into a new branch of astronomical study. Yet 3I/Atlas also highlighted humanity's limited preparedness for cosmic surprises. Despite decades of asteroid surveys designed to catalogue potentially hazardous objects, our detection networks remained optimized for predictable, gravitationally bound members of the solar system. Interstellar visitors, by definition, appeared with no advance warning, following trajectories that bypassed the orbital zones where most survey telescopes concentrated their searches. The comet's discovery trajectory illustrated this challenge perfectly. Atlas detected 3I/Atlas only when it had already penetrated deep into the solar system, well past Jupiter's orbit. Had this object been on a collision course with Earth, humanity would have received less than 3 months' warning, far too little time for any meaningful deflection attempt using current technology. NASA's Planetary Defense Coordination Office had spent years developing response protocols for asteroid impacts, including concepts for nuclear-powered interceptor spacecraft. But these plans assume detection years or decades in advance, allowing time for careful mission planning and spacecraft construction. Interstellar objects challenged these assumptions by arriving unannounced and departing rapidly, often visible for only months before fading beyond detection limits. Dr. Lindley Johnson, NASA's Planetary Defense Officer, acknowledged the implications during a press briefing following the discovery announcement. Interstellar objects represent a new category of potential impact threats that we're only beginning to understand. Unlike asteroids with predictable orbits, these visitors give us no advance warning and often very little time to study them before they're gone. The chemical composition of 3I/Atlas added another layer of complexity to future considerations. Its carbon dioxide-rich nature suggested different sublimation patterns than typical solar system comets, potentially creating debris trails with unfamiliar characteristics. Should future interstellar visitors arrive on Earth-crossing trajectories, their alien chemistry might produce atmospheric interactions unlike anything in our experience. Historical precedent offered little guidance. Earth's geological record preserved evidence of numerous asteroid and comet impacts over billions of years, but none clearly identified as interstellar in origin. The rarity of such impacts, combined with the difficulty of distinguishing interstellar from solar system impactors in ancient crater records, left scientists without empirical data about the effects of alien chemistry entering Earth's atmosphere. As 3I/Atlas continued its journey through the inner solar system, research groups worldwide initiated observing campaigns to maximize scientific return from this unexpected visitor. The European Southern Observatory's Very Large Telescope in Chile detected cyanide gas and atomic nickel vapor in the comet's coma, molecules common in solar system comets, but representing the first such detections in an interstellar visitor. These measurements provided crucial data for understanding comet formation processes around other stars. The presence of familiar molecules suggested that planet formation mechanisms operated similarly across different stellar systems, while the unusual abundance ratios revealed subtle differences in formation conditions that existed billions of years ago around an alien sun. The Hubble Space Telescope contributed high-resolution images that allowed astronomers to estimate the nuclear size of 3I/Atlas. Analysis suggested a diameter between 320 meters and 5.6 kilometers, with the most probable size being less than 1 kilometer. This relatively small nucleus explained why the comet had remained undetected until its close approach to the Sun triggered sufficient activity to create a visible coma. By August, 3I/Atlas had developed a distinctive tail pointing away from the Sun, created by solar radiation pressure pushing dust particles ejected from the nucleus. Amateur astronomers with modest telescopes could now observe this interstellar visitor directly, marking the first time in human history that ordinary observers could witness material from another star system with their own eyes. The comet's brightness peaked in September before beginning its fade toward invisibility. As 3I/Atlas disappeared behind the Sun's glare in late September, astronomers prepared for its reappearance in early December, when the comet would emerge on the opposite side of the Sun, racing away from the inner solar system forever. This brief window represented humanity's only opportunity to study 3I/Atlas directly. Unlike solar system comets that return predictably over centuries or millennia, this interstellar wanderer would continue accelerating away from the Sun, eventually returning to the cold darkness between the stars. In perhaps 50,000 years, 3I/Atlas might encounter another stellar system and briefly warm again, but for human civilization, this passage marked a unique, unrepeatable encounter. The discovery of 3I/Atlas thus served as both scientific windfall and sobering reminder. While the comet posed no threat to Earth, its unexpected appearance highlighted humanity's cosmic vulnerability. We exist in a universe where objects can arrive without warning from the depths of space, carrying alien chemistry and unknown properties into our familiar solar system. As 3I/Atlas faded into the distance, carrying its cargo of extraterrestrial molecules back toward interstellar space, it left behind more than scientific data. It demonstrated that our solar system remained open to visitors from across the galaxy, and that Earth's isolation in cosmic terms was merely temporary. The next stranger at the gate might arrive tomorrow, next year, or next century. We simply could not know when, from where, or carrying what. In this age of global connectivity and technological sophistication, 3I/Atlas reminded us that some challenges still arrived from directions we could not anticipate, at speeds we could not match, bearing properties we were only beginning to understand. The universe, it seemed, still held surprises for anyone willing to watch the night sky with sufficient care and appropriate humility. Consider a grain of sand drifting through the vacuum of space. This microscopic particle, no larger than what might slip between your fingers on a beach, carries within itself the memory of another world. It originated from the nucleus of an interstellar comet, ejected by solar heat as the icy visitor approached our Sun. Now it follows its own trajectory, invisible to telescopes, joining countless billions of similar fragments in what scientists call a debris trail. When 3I/Atlas rounded the Sun in late October 2025, it shed material continuously. Solar heating sublimated water ice, carbon dioxide, and exotic compounds from its surface, creating the characteristic coma and tail visible to observers on Earth. But this spectacular display represented only the beginning of a longer story. The particles that escaped the comet's weak gravity would continue traveling through space long after their parent object had departed our solar system. Dr. Peter Brown of Western University in Ontario has spent decades studying how cosmic debris moves through the solar system. His research on meteor streams reveals the hidden architecture of space, invisible highways of particles that mark the ancient passages of comets. Every comet leaves a trail, he explains. These trails can persist for thousands of years, spreading along the original orbital path like a cosmic breadcrumb trail. For solar system comets, this process creates predictable meteor showers when Earth intersects their debris streams. The Perseids in August mark our planet's annual passage through particles left by Comet Swift-Tuttle. The Leonids in November result from debris shed by Comet Tempel-Tuttle over centuries of passages. These familiar displays follow orbital mechanics that allow astronomers to predict their timing and intensity with remarkable precision. Interstellar debris presents a fundamentally different challenge. Unlike bound comets that return periodically, interstellar visitors like 3I/ATLS follow hyperbolic trajectories that carry them through the solar system once and never again. Their debris trails stretch behind them like wake behind a ship, but these wakes extend across interstellar distances and persist for millions of years. The physics of particle ejection determines how this debris spreads. When solar heating vaporizes material from a comet nucleus, the expanding gas carries dust particles away at velocities ranging from meters per second to several kilometers per second. The smallest particles pushed by radiation pressure from sunlight can achieve speeds exceeding the comet's own orbital velocity. Larger fragments maintain trajectories closer to their parent object's path. This velocity distribution creates what researchers call a debris envelope, a three-dimensional region of space containing particles of various sizes, moving at slightly different speeds and directions. Over time, this envelope expands and elongates, transforming from a relatively compact cloud into a vast diffuse stream stretching across astronomical distances. Mathematical models developed by researchers at NASA's Goddard Space Flight Center suggest that debris from 3I/ATLS will continue diverging long after the comet itself has returned to interstellar space. The smallest particles, influenced by solar radiation pressure and planetary gravitational fields, may achieve trajectories that carry them throughout the solar system. Some could even achieve solar escape velocity, joining the interstellar medium as independent wanderers. Dr. Apostolos Christou of the AMA Observatory and Planetarium has modeled how interstellar debris behaves differently from solar system material. The key difference is permanence. He notes, solar system comet debris gets recycled. Particles eventually collide with planets, fall into the sun, or get ejected by planetary encounters. Interstellar debris just keeps going, spreading outward forever. The implications become significant when considering what happens if Earth encounters such a debris stream. Unlike familiar meteor showers that last for days or weeks, an interstellar debris encounter could persist for months or even years, depending on how the trail has spread since its parent comet's passage. Atmospheric entry dynamics reveal why this extended encounter could prove problematic. When particles enter Earth's atmosphere at typical meteor velocities of 20 to 70 kilometers per second, they create brilliant streaks of light as atmospheric friction vaporizes the incoming material. The energy release heats surrounding air to thousands of degrees, creating the luminous plasma trails we observe as meteors. Individual particles from 3I/ATLS debris would likely be too small to create visible meteors. Research by meteor physicist Dr. Margaret Campbell Brown suggests that most interstellar comet debris consists of particles smaller than 1 millimeter in diameter, too tiny to generate detectable light when entering the atmosphere. Instead, they would be absorbed silently, adding their alien chemistry to Earth's upper atmosphere without fanfare. But quantity matters more than individual visibility. Computer simulations indicate that a typical comet's nucleus 10 kilometers in diameter could produce more than 10 to the 15th power individual particles during its passage through the inner solar system. For 3I/ATLAS, with its estimated diameter of less than 1 kilometer, the number drops to perhaps 10 to the 13th particles, still an astronomical quantity by human standards. Should Earth encounter a dense region of this debris stream, the cumulative effect could prove significant. Billions of microscopic particles entering the atmosphere simultaneously would deposit their alien chemistry across the entire planet. The metallic content of these particles, iron, nickel, magnesium, and trace elements formed around another star, would be distributed throughout the upper atmosphere and eventually settle to the surface. Dr. Susan Taylor of the Cold Regions Research and Engineering Laboratory has studied how cosmic dust affects Earth's atmospheric chemistry. Her analysis of ice cores from Greenland reveals layers containing elevated concentrations of cosmic materials, marking periods when Earth encountered unusual amounts of extraterrestrial debris. The atmosphere is constantly receiving cosmic input, she explains. But the composition of that input varies dramatically depending on its source. Interstellar debris carries isotopic signatures that distinguish it from solar system material. Elements formed in the nuclear furnaces of other stars bear the chemical fingerprints of different stellar evolution processes. Iron-60, an isotope with a half-life of 2.6 million years, serves as a particularly clear marker of material from recent nearby supernova. Enhanced concentrations of such isotopes in atmospheric deposits would provide unmistakable evidence of interstellar origin. The biological implications remain largely unexplored. Earth's atmosphere has evolved over billions of years in the presence of solar system cosmic dust, which maintains relatively consistent chemical and isotopic properties. Introducing large quantities of alien material with different compositions could potentially affect atmospheric chemistry in unexpected ways. Some researchers speculate that interstellar organic compounds might survive atmospheric entry under specific conditions. Complex molecules like amino acids and nucleotides, if protected within larger particles or ice grains, could potentially reach Earth's surface intact. This scenario resurrects ancient questions about panspermia, the hypothesis that life spreads between worlds on cosmic debris. Dr. Chandra Wickramasinghe of the Centre for Astrobiology at the University of Buckingham has long advocated for interstellar transfer of biological material. Comets are natural spacecraft, he argues. They can preserve organic compounds and even living microorganisms across interstellar distances. When these materials enter planetary atmospheres, they seed worlds with the chemical precursors or even the organisms needed for life to begin. The discovery of complex organic molecules in interstellar space lends credence to such possibilities. Radio telescopes have detected more than 200 different molecular species in interstellar clouds, including sugars, alcohols, and compounds containing carbon-nitrogen bonds essential for life. If 3I/Atlas formed in a chemically rich environment around its parent star, its debris could carry similar organic complexity. Laboratory experiments conducted by Dr. John Briccato at the Astrophysical Observatory of Arcetri demonstrate that organic compounds can indeed survive simulated atmospheric entry conditions. When researchers subjected amino acid samples to temperatures and pressures comparable to meteor entry, they found that significant fractions of the organic material remained intact, particularly when protected within mineral matrices. The temporal aspect adds another dimension to the debris trail phenomenon. Unlike the discrete passages of returning comets, interstellar debris streams could interact with Earth's orbit for extended periods, Computer models suggest that debris from 3I/ATLS might continue intersecting Earth's orbital path for centuries, creating recurring episodes of enhanced cosmic dust influx. Such extended exposure raises questions about cumulative effects. While individual encounters with interstellar debris might produce only subtle atmospheric changes, repeated exposure over decades or centuries could lead to measurable modifications in atmospheric chemistry. The detection of such changes would require careful monitoring programs capable of distinguishing interstellar inputs from the constant background of solar system cosmic dust. Current atmospheric monitoring systems, designed primarily to track human-produced pollutants and natural variations, lack the sensitivity and specificity needed to detect interstellar debris signatures. Upgrading these networks to include isotopic analysis capabilities could provide early warning of unusual cosmic dust events and help scientists understand how alien material affects Earth's atmosphere. The debris trail phenomenon also highlights gaps in our understanding of interstellar object populations. If 3I/ATLS represents a typical example of interstellar comets, and if such objects visit the inner solar system regularly, then Earth may be receiving continuous inputs of alien material from multiple sources. The cumulative effect of numerous interstellar debris streams could be shaping atmospheric evolution in ways we have not recognized. Dr. Abraham Loeb of Harvard University suggests that improved detection capabilities might reveal interstellar debris streams as a common feature of galactic neighborhoods. We're only beginning to appreciate how connected planetary systems are through the exchange of material, he notes. What we consider pristine solar system environments may actually be contaminated by debris from countless other stellar systems. This perspective transforms our understanding of Earth's chemical isolation. Rather than existing in a closed system dominated by solar system processes, our planet may be continuously sampling material from across the galaxy. Each interstellar visitor, like 3I/ATLS, contributes to this cosmic mixing, adding alien chemistry to Earth's evolving atmospheric composition. The implications extend beyond atmospheric science to questions of planetary evolution and the origin of life. If interstellar debris has been enriching Earth's atmosphere throughout geological time, it may have played unrecognized roles in chemical evolution and possibly even biological development. The complex organic compounds detected in interstellar space could have been raining down on early Earth, providing raw materials for the emergence of life. As 3I/ATLS continues its journey away from the inner solar system, it leaves behind more than scientific measurements and spectroscopic data. It has deposited an invisible legacy, billions of microscopic particles that will continue drifting through space long after the comet itself has returned to the darkness between stars. These particles carry with them the chemistry of an alien world, destined to spread throughout the solar system and perhaps eventually settle onto planetary surfaces. Some of these particles may already be entering Earth's atmosphere, adding their microscopic contribution to the cosmic dust that rains down continuously from space. Others will follow more complex trajectories, influenced by gravitational encounters with planets and the pressure of solar radiation, before eventually finding their own paths through the solar system. In this way, 3I/ATLS demonstrates that interstellar visits are never truly temporary. While the main body of the comet departs and fades from view, pieces of its alien substance remain behind, integrated forever into the chemical inventory of our solar system. We are all, in a very literal sense, made partially of star stuff, and now we know that some of that star stuff originated around other stars, delivered to us by cosmic wanderers like 3I/ATLS. The invisible rivers of debris flowing through space connect us to the broader galaxy in ways both subtle and profound. Each microscopic particle carries messages from distant worlds, written in the language of atomic structure and molecular bonds. Learning to read these messages may ultimately teach us as much about the universe as the spectacular comets that deliver them. In the sterile environment of the International Space Station's Japanese experiment module, a petri dish containing bacteria from Earth has been exposed to the vacuum of space for exactly 365 days. Akihiko Yamagishi retrieves the sample, expecting to find nothing but dead microorganisms. Instead, under the microscope, clusters of Deinococcus radiodurans cells show clear signs of life. They have survived 12 months of cosmic radiation, temperature extremes ranging from -150 to +120 degrees Celsius, and the complete absence of liquid water. This experiment, conducted in 2020, proved that terrestrial life could endure far longer in space than previously imagined. But it also raised a disturbing question. If Earth bacteria could survive such conditions, what about microorganisms that evolved elsewhere in the galaxy? Could 3I/Atlas be carrying living passengers from another world? The concept of panspermia, life spreading between planets on natural spacecraft like comets and asteroids, has fascinated scientists since the late 19th century. Swedish chemists Svante Arrhenius first proposed that bacterial spores might travel between worlds, but his original hypothesis assumed individual organisms drifting through space unprotected. Modern understanding suggests a more plausible mechanism: microorganisms sheltered within the protective matrix of cosmic debris. Dr. Gerda Horneck of the German Aerospace Center has conducted extensive research on microbial survival in space environments. Her experiments demonstrate that bacteria can withstand conditions far more extreme than those found on any planetary surface. The key factors for survival are protection from ultraviolet radiation and cosmic rays, plus some form of desiccation resistance, she explains. Many extremophile bacteria possess both characteristics naturally. Deinococcus radiodurans, nicknamed Conan the Bacterium by researchers, represents the most radiation-resistant organism known to science. This remarkable microbe can survive radiation doses 2,000 times greater than what would kill a human being. Its DNA repair mechanisms can reconstruct completely shattered chromosomes from hundreds of fragments, essentially rebuilding its genetic code after devastating damage. But radiation resistance alone does not guarantee interstellar survival. The journey between star systems requires millions of years, during which cosmic rays gradually accumulate damage faster than even the most robust repair mechanisms can correct. However, bacteria rarely travel alone in nature. They form communities, aggregate into protective clusters, and often embed themselves within mineral matrices that provide additional shielding. Research conducted by Dr. Rocco Mancinelli at NASA's Ames Research Center reveals that bacterial communities can survive conditions impossible for individual organisms. When bacteria aggregate into dense clusters, the outer layers sacrifice themselves to protect the interior population from radiation. This protective strategy, combined with cryptobiosis, a state of suspended animation, could theoretically allow microbial communities to survive interstellar journeys. The discovery of organic compounds throughout interstellar space adds credibility to these survival scenarios. Radio telescopes have detected complex molecules, including glycine, the simplest amino acid, in the interstellar medium. If simple organic compounds can persist in the harsh environment between stars, more complex structures like bacterial spores might also endure the journey, particularly when protected within cometary ice. 3I/Atlas presents unique characteristics that make it an ideal candidate for carrying alien microorganisms. Its carbon dioxide-rich composition suggests formation in the cold outer regions of another star system, where organic compounds remain stable for billions of years. The comet's unusual chemistry, including carbonyl sulfide and other sulfur-bearing molecules, might reflect biological processing that occurred on or within its parent body. Dr. Chandra Wickramasinghe of the University of Buckingham has long advocated for biological explanations of comet composition. His analysis of spectroscopic data from various comets reveals signatures consistent with organic polymers and even bacterial cellulose. The infrared spectra of comet dust match remarkably well with dried bacteria, he argues. This could be coincidence, or it could indicate that comets actually contain biological material. The survival requirements for interstellar bacteria become less daunting when considered from an evolutionary perspective. Any microorganisms that successfully travel between star systems must have evolved in environments that prepared them for the journey: planets orbiting dying stars, worlds stripped of their atmospheres by stellar winds, or organisms ejected from habitable moons might already possess the extreme survival traits needed for interstellar travel. Consider the environment around red dwarf stars, which comprise roughly 75% of all stars in the galaxy. These dim, long-lived suns often produce powerful flares that strip away planetary atmospheres and irradiate surfaces with sterilizing radiation. Microorganisms that evolved on such worlds would necessarily develop extraordinary resistance to radiation, desiccation, and temperature extremes, precisely the traits needed for survival in interstellar space. The ejection mechanism itself might select for the hardiest organisms. When asteroids or comets impact planetary surfaces, they excavate material from depths where extremophile bacteria typically thrive. These subsurface communities already live in conditions resembling those found in interstellar space: minimal water availability, intense radiation, and extreme temperature variations. Impact ejection might simply transfer them from one extreme environment to another. Dr. J. Melosh of Purdue University has modeled the physics of impact ejection and bacterial survival. His calculations suggest that rock fragments blasted from planetary surfaces can retain temperatures low enough to preserve organic compounds and even living organisms. The center of a large ejector block can remain cool even while the surface melts, he notes. Bacteria embedded in such material could survive both the ejection event and subsequent interstellar travel. The arrival of 3I/ATLS in our solar system provides an unprecedented opportunity to test these theories. Unlike previous interstellar visitors that were detected too late for detailed study, 3I/ATLS remained visible for months, allowing researchers to analyze its composition and search for potential biological signatures. Spectroscopic observations by the James Webb Space Telescope revealed complex organic chemistry within 3I/ATLS's coma. The presence of carbon-bearing molecules, including those containing nitrogen and sulfur, suggests chemical processes that could support or result from biological activity. While these signatures do not prove the presence of living organisms, they demonstrate that 3I/ATLS contains the chemical building blocks of life. The European Space Agency's planned Comet Interceptor mission, designed to study a pristine comet from the Oort cloud, originally intended to analyze solar system materials. However, mission planners are now considering whether future interstellar visitors like 3I/ATLS might make even more valuable targets. Such a mission could deploy instruments capable of detecting biological signatures, including amino acid chirality, isotopic ratios, indicating biological processing, and even direct microscopic examination of comet material. The implications of discovering alien microorganisms would extend far beyond astrobiology. Living organisms from another star system would carry genetic information that could revolutionize our understanding of life's diversity and evolution. DNA or RNA sequences from alien bacteria might reveal completely different approaches to information storage and replication, expanding our conception of what life can achieve. But the discovery would also raise immediate practical concerns. Alien microorganisms, even if benign in their original environment, could potentially disrupt Earth's ecosystems in unpredictable ways. They might carry metabolic pathways unknown to terrestrial life, produce toxins for which Earth organisms have no resistance, or simply outcompete native species through superior adaptation to extreme conditions. Dr. Margaret Race of the SETI Institute has extensively studied the protocols needed for handling extraterrestrial samples. We have detailed planetary protection procedures for missions to Mars and other potentially habitable worlds, she explains. But we're less prepared for alien material that comes to us. Interstellar objects present unique challenges because we can't control when they arrive or what they contain. The atmospheric entry of 3I/ATLS debris adds another layer of complexity to these considerations. While the main body of the comet passed safely by Earth, microscopic particles from its coma and tail could theoretically enter our atmosphere over extended periods. If these particles contain viable microorganisms, they would be distributed globally without any human control or containment. Mathematical models suggest that atmospheric heating during entry would likely sterilize most organic material. Temperatures exceeding several thousand degrees Celsius should destroy any biological structures, breaking down complex molecules into their constituent atoms. However, the largest particles might retain cool interiors during brief atmospheric passages, potentially allowing some material to survive to the surface. The question becomes whether alien bacteria could adapt quickly enough to survive in Earth's environment. Terrestrial extremophiles demonstrate remarkable flexibility, thriving in environments from boiling hot springs to Antarctic ice sheets. Organisms that survived millions of years in interstellar space might possess even greater adaptability, allowing them to establish themselves in Earth's diverse ecosystems. Historical precedent offers little guidance. Earth's geological record preserves evidence of numerous mass extinctions, but none clearly linked to biological contamination from space. The absence of such evidence might simply reflect the rarity of successful interstellar biology, the difficulty of detecting ancient biological invasions, or the possibility that such events have not yet occurred during Earth's history. The discovery of extremophile bacteria in Earth's most hostile environments continues to expand our understanding of life's limits. Organisms thrive in sulfuric acid hot springs, beneath miles of Antarctic ice, in deep ocean trenches, and even within radioactive waste sites. Each new discovery pushes the boundaries of what scientists consider habitable, making interstellar survival seem increasingly plausible. Recent research has identified bacterial communities living in clouds, surviving and reproducing in the upper atmosphere, despite intense ultraviolet radiation and severe desiccation. These aerial bacteria demonstrate that life can persist in environments previously considered sterile. If terrestrial organisms can survive in Earth's upper atmosphere, alien bacteria might find the transition from interstellar space to planetary environments less challenging than previously assumed. The temporal aspect of interstellar biology adds another dimension to consider. While the journey between star systems requires millions of years, bacterial communities on Earth have demonstrated the ability to remain dormant for extraordinary periods. Researchers have revived bacteria from samples hundreds of thousands of years old, suggesting that properly preserved microorganisms could potentially survive even interstellar travel times. As 3I/ATLAS continues its departure from the solar system, it carries with it any biological secrets it might harbour. The comet's brief passage through our neighbourhood provided tantalising glimpses of alien chemistry and complex organic compounds, but definitive answers about possible biological content remain elusive. Future interstellar visitors might offer better opportunities for biological investigation, particularly if we detect them early enough to plan dedicated study missions. The microbial arc theory transforms our understanding of cosmic exploration. Rather than sterile chunks of rock and ice wandering between stars, comets like 3I/ATLAS might serve as natural spacecraft carrying the genetic heritage of distant worlds. Each interstellar visitor becomes a potential messenger, bringing not just chemical information about alien star systems, but possibly life itself. Whether 3I/ATLAS carried living passengers remains unknown, but its passage through our solar system has demonstrated that interstellar objects possess the chemical complexity needed to support life and the physical characteristics required to protect delicate organic structures during their journey through space. In this sense, every interstellar visitor represents both a scientific opportunity and a biological uncertainty, a microscopic arc that might be carrying the seeds of life from another world. The universe, it seems, may be far more biologically connected than we ever imagined. If the microbial arc theory proves correct, then life spreads throughout the galaxy not through deliberate exploration, but through the patient, persistent wandering of cosmic debris. We exist not on an isolated world, but on a planet continuously sampling the biological diversity of countless other star systems, one microscopic passenger at a time. The control room at NASA's Planetary Defense Coordination Office maintains a constant vigil, monitoring threats that could emerge from the depths of space with little warning. Banks of computers process data from telescopes worldwide, tracking thousands of near-Earth objects whose orbits might someday intersect our planet's path. But on this particular morning in November 2025, the screens display a sobering reality. Every current planetary defense system was designed for threats that announce themselves years or decades in advance. 3I/ATLAS had provided just over 3 months of warning from discovery to closest approach. Had this interstellar visitor been on a collision course with Earth, humanity would have faced an unprecedented challenge. How do you deflect an object when there's no time to build and deploy the spacecraft needed for the mission? Dr. Lindley Johnson has spent his career preparing for cosmic impacts. As NASA's former planetary defense officer, he understands both the capabilities and limitations of current protection systems. Our entire deflection strategy depends on early detection, he explains. We need years to plan a mission, build the spacecraft, launch it, and execute the deflection maneuver. Months simply isn't enough time. The mathematics of spacecraft trajectories reveal the fundamental challenge. A successful deflection mission requires precise timing and enormous amounts of energy. To change an asteroid's orbit enough to miss Earth, a spacecraft must either impact the object directly at tremendous velocity or position itself nearby to provide gentle but persistent gravitational nudging over extended periods. Both approaches require years of advanced planning. The Double Asteroid Redirection Test mission, successfully executed in 2022, demonstrated humanity's ability to alter an asteroid's trajectory through kinetic impact. DART's spacecraft struck the small moon Dimorphos orbiting the asteroid Didymos, changing its orbital period by 32 minutes. This proof of concept validated deflection theory, but the mission required 4 years from conception to impact, plus precise knowledge of the target's characteristics and orbital mechanics. For interstellar objects like 3I/Atlas, such leisurely preparation becomes impossible. These cosmic wanderers follow hyperbolic trajectories that carry them through the inner solar system in a matter of months. By the time telescopes detect them, they've already passed Jupiter's orbit and are rapidly approaching their closest point to the Sun. Any deflection attempt must be executed quickly, with limited knowledge of the object's composition, structure, and rotation state. Dr. Joseph Nuth of NASA's Goddard Space Flight Center has proposed a radical solution to this timing problem: stored interceptor spacecraft maintained in constant readiness for immediate deployment. We need planetary defense assets already built and waiting, he argues. When an interstellar threat appears, we launch within days, not years. This interceptor concept envisions a network of powerful spacecraft parked at strategic locations throughout the solar system, equipped with nuclear propulsion systems capable of reaching any incoming object within weeks of detection. Each interceptor would carry sufficient payload to alter the trajectory of objects up to several kilometers in diameter through direct kinetic impact. The engineering challenges are formidable. Nuclear thermal or nuclear electric propulsion systems offer the only realistic means of achieving the velocities needed to intercept fast-moving interstellar objects. Chemical rockets, which power current spacecraft, simply cannot generate enough energy to match the speed and trajectory changes required for rapid interception missions. Russia's nuclear-powered spacecraft development program, initiated in the early 21st century, provides a glimpse of the technology required. Their nuclear thermal designs achieve specific impulses twice that of chemical rockets, dramatically reducing the fuel mass needed for high-energy missions. However, these systems remain experimental, with significant technical hurdles still to overcome. The storage and maintenance of interceptor spacecraft present additional complications. Nuclear-powered systems require constant monitoring and periodic maintenance to ensure readiness. Fuel systems degrade over time, electronic components fail due to radiation exposure, and structural materials suffer fatigue from thermal cycling. Maintaining a fleet of ready interceptors would cost billions of dollars annually. Beyond technical challenges, the deflection dilemma multiplies when considering not a single interstellar visitor, but a swarm of objects arriving simultaneously. Computer simulations of the 3I/Atlas scenario suggest that if this comet were followed by numerous smaller companions, the result could overwhelm any conceivable defense system. Dr. Alan Harris of the German Aerospace Center has modeled multi-object deflection scenarios. His calculations reveal the mathematical impossibility of defending against simultaneous threats arriving from different directions. Each deflection mission requires a dedicated spacecraft trajectory, he notes. You can't use one interceptor to address multiple targets. The orbital mechanics simply don't allow it. The problem becomes even more complex when considering the diversity of interstellar objects. Unlike well-studied solar system asteroids and comets, interstellar visitors arrive with unknown compositions and structures. 3I/Atlas's unusual CO2-rich chemistry suggests different physical properties than typical solar system comets. Its density, strength, and internal structure remain largely unknown, making deflection calculations highly uncertain. Successful deflection requires understanding how much momentum transfer is needed to alter the object's trajectory sufficiently to miss Earth. This calculation depends critically on the object's mass, which in turn depends on its size, density, and internal structure. For interstellar objects detected only months before potential impact, such detailed characterization becomes nearly impossible. The rotation state of incoming objects adds another variable to deflection calculations. Many asteroids and comets tumble chaotically as they travel through space, rotating around multiple axes simultaneously. The effectiveness of a kinetic impact depends strongly on where and when the spacecraft strikes the spinning target. Poor timing could result in ineffective momentum transfer or even fragmentation that creates multiple smaller threats. Dr. Nancy Chabot of the Johns Hopkins Applied Physics Laboratory, who led the DART mission, emphasizes the importance of target characterization. "We spent years studying didymos and dimorphos before impact," she explains. "We knew their orbital mechanics, rotation periods, and approximate compositions. For an interstellar object discovered 3 months before potential impact, we'd have none of that crucial information." The energy requirements for deflecting interstellar objects exceed those for solar system threats by substantial margins. Interstellar visitors carry enormous kinetic energy due to their high velocities relative to the solar system. 3 I/ATLAs approached at approximately 60 km per second, compared to typical asteroid velocities of 20 to 25 km per second. The energy needed to deflect such fast-moving objects scales with the square of their velocity, making interstellar deflection missions exponentially more difficult. Nuclear weapons represent the only current technology capable of delivering sufficient energy for deflecting large interstellar objects on short notice. The Comprehensive Test Ban Treaty prohibits nuclear testing in space, but emergency exceptions might be possible for planetary defense scenarios. However, using nuclear explosives for deflection introduces additional complications and risks. The optimal strategy for nuclear deflection involves detonating the weapon near the object's surface rather than within it, using X-ray radiation and debris from the explosion to vaporize surface material and create thrust through material ejection. This approach requires precise timing and positioning to avoid fragmenting the object into multiple pieces that could still threaten Earth. Dr. David Dearborn of Lawrence Livermore National Laboratory has extensively modeled nuclear deflection scenarios. His simulations suggest that properly executed nuclear deflection could alter the trajectory of kilometer-sized objects even with relatively short warning times. However, the technique remains untested and carries significant risks of unintended consequences. International cooperation presents another challenge for rapid deflection missions. Current planetary defense protocols assume years of preparation time, allowing for extensive diplomatic coordination and shared mission planning. Interstellar objects arriving with months of warning would require unprecedented speed in international decision-making and resource coordination. The legal framework for planetary defense remains underdeveloped, particularly for nuclear deflection missions. Who has the authority to deploy nuclear weapons in space for planetary defense? How are decisions made about deflection strategies when multiple nations possess relevant capabilities? These questions become urgent when dealing with imminent threats that allow no time for extended negotiations. Economic considerations add another layer to the deflection dilemma. The cost of maintaining a ready interceptor fleet would rival current space budgets of major nations. The International Space Station, humanity's most expensive space project, cost roughly $150 billion over its development and operational lifetime. A comprehensive interstellar defense system would likely cost several times more. Insurance models developed for asteroid impact scenarios suggest that the economic damage from a major impact could exceed global GDP for multiple years. From this perspective, even extremely expensive defense systems might prove cost-effective. However, the probability of any specific interstellar object threatening Earth remains low, making it difficult to justify massive expenditures for low-probability events. Private sector involvement could potentially address some economic challenges. Companies like SpaceX and Blue Origin have demonstrated capabilities for building and launching spacecraft at costs substantially lower than traditional government programs. Public-private partnerships might enable more affordable development and maintenance of interceptor systems. The detection aspect of planetary defense faces similar timing challenges. Current survey telescopes like ATLAS and Catalina Sky Survey excel at finding solar system objects that follow predictable orbital patterns. Interstellar objects appear without warning, often in sky regions not regularly monitored by existing surveys. By the time they're detected, they've already penetrated deep into the inner solar system. The Vera Rubin Observatory, scheduled for full operations in the coming years, will survey the entire southern sky every few nights, dramatically improving detection capabilities for transient objects. However, even this advanced system might provide only weeks or months of warning for rapidly moving interstellar threats. Space-based detection systems could potentially provide earlier warning by observing from locations with unobstructed views of the entire sky. The proposed Sentinel mission, designed to detect Earth-threatening asteroids from Venus orbit, could serve as a model for interstellar object detection. However, such systems would require substantial international investment and cooperation. The deflection dilemma ultimately reflects humanity's position as a cosmic newcomer. We have developed impressive technological capabilities, but only recently begun to comprehend the scale and complexity of cosmic threats. Our planetary defense systems evolved to address familiar, predictable dangers from within our own solar system. Interstellar visitors like 3 I/ATLAs force us to confront the possibility of threats that arrive without warning, carrying unknown properties, and requiring response capabilities we do not yet possess. As 3 I/Atlas faded into the distance, it left behind more than scientific data and spectacular images. It demonstrated that our cosmic neighborhood remains fundamentally unpredictable, filled with visitors whose arrival schedules and intentions we cannot anticipate. The deflection dilemma it highlighted has no easy solutions, only the sobering realization that some cosmic challenges may exceed our current ability to address them. The next interstellar visitor might give us decades of warning, allowing careful study and measured response. Or it might arrive on a trajectory that provides only weeks between detection and potential impact. In either case, 3 I/ATLAS has shown us that the universe still holds surprises for which we are not yet prepared, and that our planetary defense capabilities must evolve to match the cosmic realities we are only beginning to understand. Above the remote Canadian wilderness, a brilliant streak of light tears across the pre-dawn sky. Meteor cameras operated by Western University capture the event in precise detail. An object roughly 2 meters in diameter enters Earth's atmosphere at 67 kilometers per second, creating a fireball visible across 3 provinces. Within seconds, atmospheric friction converts the incoming mass into superheated plasma, light, and eventually microscopic dust that settles silently to the ground below. This particular fireball, observed on a clear October morning, represents the routine processing of cosmic debris by Earth's atmosphere. Our planet encounters approximately 100 tons of such material every day, most of it vaporized completely before reaching the surface. The atmosphere serves as an extraordinarily effective filter, protecting the surface from all but the largest incoming objects. But what happens when this protective system faces not individual meteoroids arriving sporadically, but thousands of objects entering simultaneously from an interstellar debris swarm? Dr. Margaret Campbell Brown of Western University studies atmospheric entry physics, analyzing how cosmic debris interacts with Earth's protective envelope. Her research reveals the delicate balance that makes our atmosphere such an effective shield. The process depends on precise energy dissipation, she explains. Objects must lose their enormous kinetic energy gradually through friction, or the result is explosive fragmentation and potentially dangerous ground impacts. The physics of atmospheric entry follow well-established principles. As an object plunges through progressively denser air, friction generates heat that vaporizes both the incoming material and surrounding atmospheric molecules. This creates a shock wave that propagates ahead of the object, compressing and heating the air to temperatures exceeding 10,000 degrees Celsius. The result is a brilliant plasma trail, the familiar streak we observe as a meteor. For objects smaller than roughly 10 centimeters in diameter, this process typically results in complete destruction well above the ground. The incoming material is converted entirely to vapor and fine dust, adding its mass to the atmosphere without reaching the surface. Larger objects can survive partial entry, arriving as meteorites that provide scientists with samples of cosmic material. The survival threshold represents a crucial boundary in atmospheric physics. Objects smaller than approximately 150 meters in diameter rarely survive intact to cause surface damage. The famous Chelyabinsk meteor of 2013, which injured over 1,000 people despite measuring only 17 meters across, exploded at an altitude of 30 kilometers, demonstrating the atmosphere's ability to contain even substantial impactors. However, these protective mechanisms assume normal encounter rates and individual objects arriving from typical directions at expected velocities. An interstellar debris swarm could potentially overwhelm the atmosphere's capacity to process incoming material safely. Computer models developed by researchers at NASA's Ames Research Center explore scenarios involving simultaneous atmospheric entries from multiple directions. The simulations reveal that when large numbers of objects enter the atmosphere within short time periods, the cumulative heating effects can create unexpected complications. Dr. Donovan Mathias leads NASA's impact modeling efforts, developing software that predicts atmospheric interactions for objects, ranging from dust grains to kilometer-sized asteroids. His models account for variables including entry angle, velocity, composition, and atmospheric density at different altitudes. Individual entries are well understood, he notes, but simultaneous multiple entries create complex interactions we're only beginning to explore. The most immediate concern involves electromagnetic effects. Each meteor creates a column of ionized plasma as it passes through the atmosphere. Under normal conditions, these plasma trails dissipate quickly without affecting electronic systems on the ground. However, numerous simultaneous entries could create widespread ionospheric disturbances similar to those produced by severe solar storms. The Tunguska event of 1908 provides historical precedent for unusual atmospheric effects from cosmic impacts. This mysterious explosion, likely caused by a small asteroid or comet fragment, created electromagnetic disturbances that affected telegraph systems across Europe and Asia. Witnesses reported unusual aurora displays and magnetic compass deflections lasting for days after the impact. Modern society's dependence on electronic systems makes electromagnetic disruption far more consequential than it was a century ago. GPS satellites, communication networks, power grids, and internet infrastructure all rely on precise electromagnetic signals that could be disrupted by widespread ionospheric disturbances. Multiple simultaneous meteor entries might create effects resembling a natural electromagnetic pulse, temporarily disabling electronic systems across large geographic regions. The thermal loading of the atmosphere presents another potential concern. Each atmospheric entry deposits enormous amounts of heat energy into the air column above the impact point. Under normal conditions, this energy disperses harmlessly into the upper atmosphere. However, if thousands of objects enter simultaneously across a broad geographic region, the cumulative heating could potentially affect local weather patterns. Dr. Apostolos Christou of the Armagh Observatory has modelled atmospheric heating from multiple simultaneous entries. His calculations suggest that widespread debris encounters could temporarily alter temperature profiles in the upper atmosphere, potentially affecting jet stream patterns and regional weather systems. The atmosphere is a coupled system, he explains. Localized heating in one region can have effects that propagate globally over time. The composition of interstellar debris adds another variable to atmospheric entry calculations. 3I/Atlas's unusual chemistry, dominated by carbon dioxide and sulfur-bearing compounds rather than typical water ice, suggests that its debris might behave differently during atmospheric entry than familiar solar system materials. Laboratory experiments conducted by Dr. Takafumi Matsui at the University of Tokyo examined how different materials respond to simulated atmospheric entry conditions. His research reveals that composition strongly influences fragmentation patterns, heat generation, and the altitude at which complete vaporization occurs. Carbon dioxide ice, for example, sublimates at much lower temperatures than water ice, potentially allowing CO2-rich debris to penetrate deeper into the atmosphere before complete destruction. The timing and geographic distribution of entries could prove as important as their total number. Debris from an interstellar swarm might arrive spread over weeks or months, following the complex orbital mechanics that govern how particles separate from their parent object over time. Alternatively, dense concentrations of material could create brief but intense episodes of multiple simultaneous atmospheric entries. Radar observations of meteor showers provide insights into how particle streams interact with Earth's atmosphere. The Geminids meteor shower, which peaks in mid-December, regularly produces over 100 visible meteors per hour at its peak. However, these particles are distributed across Earth's entire nighttime hemisphere, ensuring that any given location experiences only occasional individual entries. A concentrated interstellar debris encounter could potentially focus hundreds or thousands of entries into a much smaller geographic region and time window. The atmospheric processing capacity that easily handles globally distributed meteors might become overwhelmed when concentrated locally. The survivability of organic compounds during atmospheric entry has received increased attention following discoveries of amino acids and other complex molecules in recovered meteorites. Research by Dr. Zita Martins at Trinity College Dublin demonstrates that certain organic compounds can survive the heat and pressure of atmospheric entry when protected within mineral matrices. If interstellar debris contains organic compounds formed in alien environments, their atmospheric entry could distribute exotic chemistry across Earth's surface. While individual particles would likely be sterilized by entry heating, the sheer quantity of material from a debris swarm might allow some organic compounds to survive and reach the ground. The global distribution of this alien chemistry could potentially affect atmospheric composition on a measurable scale. Earth's atmosphere maintains a delicate chemical balance that took billions of years to establish. Large quantities of foreign materials, even if individually harmless, could theoretically perturb atmospheric chemistry in subtle but significant ways. Historical analogues for massive atmospheric disruption include major volcanic eruptions, which inject enormous quantities of dust and gas into the stratosphere. The eruption of Mount Tambora in 1815 created global climate effects lasting for years, including the famous year without a summer of 1816. While meteor swarms would deposit different materials than volcanic eruptions, the scale of atmospheric disruption could potentially produce similar consequences. The monitoring and detection of atmospheric entry events relies on networks of cameras, radar systems, and acoustic sensors distributed globally. However, these systems are designed to detect and track individual events, not massive simultaneous entries that could saturate detection capabilities. Dr. Peter Brown leads the Global Meteor Network, a worldwide system of automated cameras that monitor meteor activity. The network regularly detects and analyzes thousands of individual meteor events monthly, providing detailed data on entry velocities, trajectories, and terminal altitudes. Our systems work well for normal meteor activity, he notes, but they weren't designed to handle hundreds of simultaneous events. The data processing and analysis capabilities could become completely overwhelmed. Communication disruption during intense meteor activity presents additional challenges. Radio communications that depend on ionospheric reflection, including amateur radio, shortwave broadcasting, and some emergency communication systems, could be severely degraded by widespread ionospheric disturbances. This could complicate disaster response efforts precisely when coordination becomes most critical. The acoustic effects of multiple simultaneous atmospheric entries could create widespread sonic booms and pressure waves. The Chelyabinsk event produced shock waves that damaged buildings across a wide area, despite being a single modest-sized object. Hundreds of simultaneous entries might generate acoustic effects resembling sustained bombardment, potentially causing structural damage and public panic, even if no objects actually reach the ground. Urban areas face particular vulnerabilities during intense meteor activity. The concentration of people, electronic systems, and critical infrastructure in cities creates multiple failure points that could cascade into larger problems. Emergency response systems designed to handle individual incidents might become overwhelmed by simultaneous, widespread effects. The psychological impact of sustained meteor activity could prove as significant as physical effects. Humans evolved under skies where meteor sights were rare and generally brief. Prolonged displays of multiple simultaneous fireballs might trigger panic responses that complicate emergency management and disaster response efforts. Long-term atmospheric effects remain largely unexplored in scientific literature, while individual meteor entries leave no lasting atmospheric trace. Massive debris encounters could potentially deposit sufficient material to affect atmospheric chemistry, temperature profiles, or circulation patterns over extended periods. The adaptive capacity of Earth's atmospheric systems provides some reassurance. Our planet has endured massive volcanic eruptions, asteroid impacts, and solar storms throughout its history, with atmospheric composition and climate eventually returning to stable states. However, the timescales for recovery from major perturbations can span decades or centuries. As observers tracked 3I/ATLAs during its passage through the solar system, they witnessed not just a single visitor, but the potential harbinger of future swarm encounters. The comet's debris trail, now spreading through interstellar space, serves as a reminder that atmospheric protection systems evolved to handle individual cosmic encounters, not coordinated cosmic encounters, not coordinated cosmic assaults. The roulette metaphor captures the essential uncertainty. We cannot predict when the next interstellar debris swarm might arrive, how concentrated it might be, or whether our atmospheric defenses will prove adequate for the challenge. Each spin of the cosmic wheel brings new possibilities, some benign, others potentially overwhelming for the protective systems that have shielded Earth's surface for billions of years. The atmosphere has served as humanity's invisible guardian, silently processing cosmic debris and protecting the surface world we inhabit. But 3S/Atlas has shown us that this protection operates within limits, and that those limits might someday be tested by visitors whose nature and behavior we are only beginning to understand. High above Earth's surface, invisible lines of magnetic force stretch from pole to pole, creating a protective bubble that shields our planet from the constant stream of charged particles flowing outward from the Sun. This magnetosphere has guarded Earth for billions of years, deflecting cosmic radiation and maintaining the atmospheric conditions that make life possible. But on March 13th, 1989, this invisible shield faced a challenge that revealed its vulnerabilities. A massive solar storm struck Earth's magnetosphere with unprecedented intensity, compressing magnetic field lines and sending cascades of charged particles into the upper atmosphere. Within minutes, electrical currents induced in power transmission lines overwhelmed protective systems across Quebec, plunging 6 million people into darkness for 9 hours. The event demonstrated how electromagnetic disturbances in space could directly affect technological civilization on Earth's surface. Now, as scientists analyze the potential effects of interstellar debris swarms, they face an unsettling question. Could charged particles from alien comets create similar disruptions to Earth's magnetic environment? Dr. Janet Luhman of the University of California, Berkeley, has spent decades studying how cosmic materials interact with planetary magnetic fields. Her research on comet behavior reveals that these icy visitors carry more than just rock and frozen gases. Comets are essentially dirty snowballs that become highly conductive when solar heating creates plasma around them, she explains. They can affect local magnetic fields in ways we're still working to understand. The process begins when solar radiation heats a comet's surface, sublimating frozen compounds into expanding clouds of gas and dust. Ultraviolet light from the sun ionizes these gases, stripping electrons from atoms and creating a plasma, a state of matter consisting of electrically charged particles. This ionized material interacts strongly with magnetic fields, both the comet's own weak field and the broader magnetic environment it encounters. For comets originating within our solar system, these electromagnetic interactions follow predictable patterns. Solar system comets approach the Sun along well-characterized orbits, allowing researchers to model their plasma production and magnetic effects with reasonable accuracy. The European Space Agency's Rosetta mission, which accompanied Comet 67P Churyumov-Gerasimenko for over 2 years, provided detailed measurements of how comet plasma behaves in different solar wind conditions. Interstellar comets, like 3I/ATLAs, present fundamentally different electromagnetic challenges. These visitors carry velocities far exceeding those of solar system objects, creating much more energetic interactions when they encounter Earth's magnetic field environment. Moreover, their alien chemistry, particularly 3I/ATAlace's unusual abundance of carbon dioxide and sulfur compounds, could produce plasma with electrical properties unlike anything previously studied. The velocity factor alone makes interstellar plasma interactions potentially dangerous. When 3I/ATALAs passed through the solar system at 61 kilometers per second, any plasma it generated moved at speeds roughly 3 times faster than typical solar system comet plasma. Higher velocities mean higher kinetic energies, which translate to more powerful electromagnetic effects when charged particles interact with magnetic fields. Dr. Robert Wimmer Schweingruber of the University of Kiel studies how high-energy particles affect spacecraft and planetary environments. His research on cosmic ray interactions provides insights into what might happen when fast-moving interstellar plasma encounters Earth's magnetosphere. High-velocity charged particles can penetrate deeper into magnetic field structures, he notes. They carry enough energy to create current systems that wouldn't form under normal solar wind conditions. The chemical composition of 3I/ATALAS adds another layer of complexity to these electromagnetic considerations. Spectroscopic analysis revealed abundant carbon dioxide, carbon monoxide, and various sulfur-bearing compounds, materials that ionize differently than the water vapor that dominates most solar system comets. These different ionization properties could create plasma with unusual electrical conductivity and magnetic permeability. Laboratory experiments conducted by Dr. Geraint Thomas at Auburn University examine how different gas compositions affect plasma formation and behavior. His research shows that sulfur-bearing compounds, when ionized, create particularly dense and long-lasting plasma clouds. Sulfur ions are heavier than typical hydrogen and oxygen ions, he explains. They move more slowly and persist longer in the plasma state, potentially creating more sustained electromagnetic effects. The interaction between comet plasma and Earth's magnetosphere depends critically on the relative orientation of magnetic fields. Earth's magnetic field lines generally run from north to south, creating a dipole structure similar to a bar magnet. When incoming plasma carries magnetic fields aligned with Earth's, the interaction remains relatively benign. However, when plasma magnetic fields oppose Earth's orientation, the result can be violent magnetic reconnection events that inject enormous amounts of energy into the magnetosphere. The Carrington event of 1859 provides historical precedent for extreme magnetic reconnection. This massive solar storm created auroras visible as far south as the Caribbean and induced electrical currents strong enough to power telegraph systems even after operators disconnected their batteries. Modern analysis suggests the event resulted from solar wind plasma carrying magnetic fields anti-aligned with Earth's, creating optimal conditions for energy transfer into the magnetosphere. Interstellar plasma from objects like 3I/ATLAS could potentially create even more extreme reconnection events. The alien magnetic field orientations carried by interstellar visitors would be completely unpredictable, determined by conditions in their distant stellar birthplaces, rather than our familiar solar environment. Some configurations might prove benign, while others could create electromagnetic disturbances exceeding anything in recorded history. The technological vulnerability of modern civilization makes such electromagnetic threats far more consequential than they were in previous centuries. The power grids that failed during the Quebec blackout of 1989 represent just one component of an interconnected technological infrastructure that includes satellites, GPS navigation, cellular communications, and internet backbone systems. Dr. Daniel Baker of the University of Colorado leads research on space weather effects on technology. His studies reveal that electromagnetic pulses from magnetic storms can induce currents in any conductor exposed to changing magnetic fields. Long transmission lines act like antennas, he explains. They collect electromagnetic energy and concentrate it at transformer stations, where protective systems can be overwhelmed. Satellite systems face particular vulnerability to charged particle bombardment. The International Space Station regularly experiences computer resets and electronic glitches during solar storms. Despite sophisticated radiation shielding, commercial satellites operating in higher orbits receive even greater exposure to energetic particles, leading to component failures and operational disruptions. The Global Positioning System, which provides navigation data for everything from automobile navigation to precision agriculture, relies on atomic clocks maintained on satellites orbiting 20,000 kilometers above Earth. These orbital locations place GPS satellites directly within the magnetosphere's outer regions, where they experience the full effects of magnetic storms. Severe electromagnetic disturbances can disrupt GPS signals for hours or days, affecting transportation, communications, and financial systems that depend on precise timing. Internet infrastructure faces similar vulnerabilities through its dependence on fiber optic cable networks and cellular communication towers. While fiber optic cables themselves are immune to electromagnetic interference, the electronic equipment that processes optical signals remains vulnerable to induced currents from magnetic storms. Major internet outages could result from simultaneous failures at multiple processing nodes. The timing of interstellar plasma encounters adds unpredictability to these technological threats. Solar storms follow the roughly 11-year solar cycle, allowing some preparation for periods of increased magnetic activity. Interstellar visitors arrive without warning, potentially creating electromagnetic disturbances when technological systems are unprepared for enhanced space weather conditions. Financial markets represent a particularly vulnerable target for electromagnetic disruption. Modern trading relies on split-second communications between data centers connected by high-speed networks. Electromagnetic pulses that disrupt these connections, even temporarily, could trigger automated trading responses that cascade into market instability. The flash crash of 2010, caused by algorithmic trading responses to normal market conditions, demonstrates how technological systems can amplify small disturbances into major disruptions. Aviation systems face multiple vulnerabilities during magnetic storms. GPS navigation failures can disrupt automated flight management systems, while radio communication blackouts prevent contact between aircraft and ground control. High-altitude flights over polar regions, where Earth's magnetic field provides less protection, experience the most severe effects. During major magnetic storms, airlines routinely reroute polar flights to lower latitudes to maintain communication and navigation capabilities. The potential for cascading failures multiplies the impact of electromagnetic disruption. Modern infrastructure systems depend on each other in complex ways that can amplify the effects of individual component failures. Power grid disruptions affect communication systems, which in turn disrupt transportation networks, financial systems, and emergency response capabilities. Dr. John Kappenman, a specialist in power grid vulnerability, has modeled the potential effects of extreme magnetic storms on electrical infrastructure. His analysis suggests that a storm comparable to the Carrington event could damage hundreds of large power transformers across North America, requiring months or years for complete restoration. The electrical grid is much more vulnerable today than it was 50 years ago, he warns. We've optimized for efficiency rather than resilience. The geographic extent of magnetic storm effects depends on Earth's magnetic field geometry and the characteristics of incoming plasma. Storms typically affect higher latitudes more severely, where magnetic field lines provide direct pathways for charged particles to enter the upper atmosphere. However, extreme events can push auroral activity toward the equator, expanding the affected region to include most populated areas. Interstellar debris swarms could potentially create more widespread electromagnetic effects than typical solar storms. While solar wind plasma arrives predominantly from the direction of the Sun, creating somewhat predictable patterns of magnetic disturbance, interstellar material could encounter Earth from any direction. This could create electromagnetic effects with unfamiliar geographic patterns and duration characteristics. The recovery time from major electromagnetic disruptions varies widely depending on the systems affected and the extent of physical damage. Software-based failures typically resolve quickly once normal electromagnetic conditions return. However, physical damage to transformers, satellites, and electronic components can require weeks, months, or even years for complete replacement. Historical recovery patterns from major magnetic storms provide some guidance for preparedness planning. The Quebec blackout of 1989 required 9 hours for power restoration, but this represented a relatively modest storm by historical standards. The Halloween storms of 2003 caused satellite failures and GPS disruptions that persisted for days, while some satellite systems required months to return to full operational capacity. Hardening technological systems against electromagnetic threats requires substantial investment in shielding, backup systems, and improved protective devices. The military has extensive experience with electromagnetic pulse protection, but civilian infrastructure generally lacks such protection due to cost considerations. Retrofitting existing systems with enhanced electromagnetic protection could cost hundreds of billions of dollars globally. Early warning systems for space weather have improved dramatically in recent decades, but they remain optimized for solar storm prediction rather than interstellar threats. The Space Weather Prediction Center monitors solar activity continuously and can provide several days warning for major solar storms. However, interstellar plasma associated with objects like 3I/ATLAS would arrive with little or no advance warning. As 3I/8 departed the solar system, it left behind questions about the electromagnetic legacy of interstellar visitors. Did its passage create subtle disturbances in the solar wind that affected Earth's magnetosphere? Will future interstellar debris encounters pose greater electromagnetic threats as our technological dependence continues to grow? The magnetic storm connection reveals another dimension of cosmic vulnerability that extends beyond physical impacts or atmospheric disturbances. In our electromagnetically connected world, disturbances that occur hundreds of thousands of kilometers above Earth's surface can instantly affect technological systems that billions of people depend on for communication, navigation, power, and economic activity. Each interstellar visitor carries the potential to reveal new aspects of this electromagnetic vulnerability, testing our technological resilience with plasma conditions and magnetic field orientations that have never before encountered Earth's magnetosphere. The invisible threads of magnetic force that protect our planet may themselves become conduits for disruption when the next stranger from another star system comes calling. Deep beneath the Yucatan Peninsula, layers of limestone preserve a moment frozen in geological time. 66 million years ago, an asteroid 10 kilometers wide struck this location with the force of billions of nuclear weapons, creating the Chicxulub crater and ending the age of dinosaurs. But the rock record tells a more complex story than simple impact and extinction. It reveals how a single cosmic event triggered cascading changes that reshaped life on Earth for millions of years. Dr. Sean Gulick lowers the drill core sample under his microscope, examining the boundary layer that marks this ancient catastrophe. The rock sequence tells its story in reverse chronological order. Limestone formed in shallow seas, then a layer of impact debris mixed with the remains of a global wildfire, then more limestone from the seafloor that existed before the impact. Every centimeter represents thousands of years of Earth history, he explains. This particular centimeter represents the day the world changed forever. The geological record holds similar markers throughout Earth's history. Sudden changes in rock chemistry, fossil assemblages, and sediment composition that mark moments when cosmic visitors altered the planet's trajectory. Some represent single large impacts, while others suggest multiple simultaneous events that overwhelmed Earth's natural resilient systems. The concept of cosmic swarm impacts remains largely theoretical, but geological evidence hints at periods when Earth faced multiple threats within relatively short timeframes. The late heavy bombardment, approximately 4 billion years ago, appears to have involved numerous large impacts concentrated within a few 100 million years. While not technically simultaneous, this period demonstrates how cosmic events can cluster in ways that test planetary survival mechanisms. More recent geological layers preserve evidence of subtler, but potentially more relevant precedents. The Younger Dryas period, beginning around 12,900 years ago, marked a sudden return to Ice Age conditions after the climate had begun warming following the last glacial maximum. Some researchers propose that this climate reversal resulted from multiple comet impacts that disrupted atmospheric circulation patterns. Dr. Richard Firestone of Lawrence Berkeley National Laboratory has identified what he calls a black matte layer in sediments across North America, dating to the Younger Dryas onset. This dark layer contains elevated concentrations of platinum, microdiamonds, and other materials typically associated with cosmic impacts. The geographic distribution suggests not a single impact, but multiple events scattered across a continent-sized area. The pattern doesn't match what we'd expect from a single large impactor, Firestone notes. Instead, it looks like a swarm of smaller objects that struck across a wide region within a short time period. The cumulative effect was apparently sufficient to disrupt climate systems and trigger a return to glacial conditions. The Younger Dryas hypothesis remains controversial within the geological community, with some researchers attributing the climate changes to more mundane causes, such as volcanic activity or changes in ocean circulation. However, the debate illustrates how difficult it can be to recognize swarm impact signatures in the geological record, particularly when individual events fall below the threshold for creating obvious craters. Most cosmic impacts leave no permanent crater record. Objects smaller than roughly 50 meters typically explode in the atmosphere without reaching the surface, while impacts in ocean basins may create temporary craters that are quickly erased by sedimentation and tectonic activity. The Tunguska event of 1908, which flattened forests across 2,000 square kilometers of Siberia, left no crater despite releasing energy equivalent to several nuclear weapons. This preservation bias means that the geological record likely underrepresents the true frequency of cosmic encounters, particularly those involving swarms of smaller objects. A debris stream from an interstellar comet might create dozens of Tunguska-scale events without leaving clear geological signatures for future scientists to discover. Dr. David Kring of the Lunar and Planetary Institute studies how impact events affect Earth's geological systems. His research reveals that the consequences of cosmic impacts extend far beyond the immediate effects of explosion and crater formation. Impacts are geological reset buttons, he explains. They can alter everything from local topography to global climate patterns, with effects that persist for millions of years. The Chicxulub impact provides the most thoroughly studied example of these cascading geological effects. The initial explosion vaporized the impactor and surrounding bedrock, launching billions of tons of material into the atmosphere. Some of this debris achieved orbital velocity, circling Earth for hours before raining back down as glass spherules that heated the atmosphere and triggered global wildfires. Soot layers in the geological record preserve evidence of these worldwide fires, which consumed vegetation across entire continents and pumped enormous quantities of carbon dioxide and smoke into the atmosphere. The combination of impact debris and fire-generated particles blocked sunlight for months, creating a nuclear winter effect that caused global temperatures to plummet. But the cooling phase was temporary. As particles settled out of the atmosphere, greenhouse gases released by the impact and global fires began driving temperatures upward. The rock layers at Chicxulub contained sulfur-rich minerals that would have produced massive amounts of sulfur dioxide when vaporized by the impact. This gas eventually formed sulfuric acid aerosols that contributed to both short-term cooling and long-term ocean acidification. The marine extinction record shows how these atmospheric changes translated into biological catastrophe. Planktonic organisms that formed the base of oceanic food webs disappeared within decades of the impact, causing collapse of marine ecosystems that took millions of years to recover. On land, the sudden loss of plant photosynthesis disrupted terrestrial food webs and led to the extinction of large dinosaurs within centuries. Yet, the geological record also reveals life's remarkable resilience. Small mammals which could survive on stored food and shelter in burrows weathered the immediate crisis and subsequently diversified to fill ecological niches left vacant by extinct dinosaurs. Plant communities recovered within thousands of years, often with different species compositions that reflected changed environmental conditions. This pattern of crisis followed by recovery appears repeatedly in the geological record, suggesting that Earth's biological and geological systems possess inherent mechanisms for surviving cosmic catastrophes. However, these recovery mechanisms operate over timescales ranging from thousands to millions of years, far longer than human civilization could survive major disruption. The question of what multiple simultaneous impacts might do to these recovery mechanisms remains largely unexplored. Single large impacts, despite their devastating immediate effects, still leave intact refugia where life can persist and eventually recolonize damaged areas. Swarm impacts distributed across wide geographic areas could potentially eliminate such refugia, making recovery far more difficult. Dr. Andrew Knoll of Harvard University studies how past mass extinctions relate to environmental changes preserved in the geological record. His research suggests that extinction severity correlates with the rate and extent of environmental change, rather than simply its magnitude. Life can adapt to almost any conditions given sufficient time, he notes. But rapid, widespread changes that outpace evolutionary adaptation tend to cause mass extinctions. Interstellar debris swarms could potentially create precisely such rapid, widespread environmental changes. Unlike single impacts that create localized devastation followed by gradual global effects, simultaneous impacts across multiple continents might overwhelm the geographical isolation that allows some populations to survive and subsequently recolonize affected areas. The Deccan Traps of India provide insight into how sustained environmental stress can interact with cosmic impacts to create extinction events. These massive volcanic eruptions occurred over several 100,000 years around the time of the Chicxulub impact, releasing enormous quantities of lava and toxic gases. Some researchers suggest that the combination of volcanic stress and impact catastrophe proved more lethal than either event alone would have been. This precedent suggests that the timing of interstellar swarm encounters could prove crucial. A debris stream that arrived during a period of existing environmental stress, such as climate change, ocean acidification, or ecosystem disruption, might trigger cascading failures that would be manageable under normal conditions. Paleomagnetic studies reveal that Earth's magnetic field has undergone periodic reversals throughout geological time, leaving the planet temporarily vulnerable to increased cosmic radiation. The next interstellar visitor might arrive during such a magnetic reversal, when reduced magnetic shielding allows greater penetration of charged particles into the atmosphere and biosphere. The emerging field of astrogeology examines how cosmic events have shaped Earth's surface features and internal structure. Impact craters represent the most obvious signatures, but cosmic materials have also contributed to ore deposits, influenced volcanic activity, and affected the chemical evolution of the atmosphere and oceans. Studies of lunar samples returned by Apollo missions reveal that the Moon's surface contains materials from across the solar system, delivered by billions of years of cosmic impacts. Earth's more active geological processes erase most impact signatures, but chemical analysis of ancient rocks continues to reveal traces of extraterrestrial materials integrated into our planet's structure. The isotopic signatures of cosmic materials provide particularly sensitive indicators of past impact events. Elements like osmium and platinum exist in much higher concentrations in cosmic debris than in Earth's crustal rocks. Spikes in these elements within sedimentary sequences often mark impact events, even when no crater remains to provide obvious evidence. Dr. Franco Marcantonio of Texas AANDM University analyzes these isotopic signatures in marine sediments to identify cosmic input events throughout Earth's history. His research suggests that significant cosmic material additions occur more frequently than crater counting would indicate, implying that many impacts go unrecognized in traditional geological surveys. The chemical record is much more sensitive than the physical record, he explains. We can detect cosmic input events that left no craters but still contributed measurable amounts of extraterrestrial material to Earth's surface environment. This enhanced sensitivity to cosmic signatures raises intriguing questions about the frequency and significance of past swarm encounters. Sedimentary layers that show multiple closely spaced isotopic anomalies might represent debris streams from ancient interstellar visitors, their signatures preserved long after any physical impact features have been erased. The Precambrian geological record, covering the first 4 billion years of Earth history, contains numerous unexplained isotopic anomalies and abrupt changes in atmospheric composition. Some of these features might represent encounters with interstellar debris streams that occurred when Earth's geological processes were different enough to preserve signatures that would be quickly erased today. Climate proxy records derived from ice cores, tree rings, and sediment cores provide additional archives of past environmental changes that might reflect cosmic encounters. Sudden temperature changes, precipitation pattern shifts, and atmospheric chemistry alterations could all potentially result from debris stream encounters that fell below the threshold for creating obvious geological signatures. The Greenland ice cores analysed by Dr. Lonnie Thompson preserved detailed records of atmospheric conditions over the past 100,000 years. These archives contain numerous brief climate anomalies that last only decades or centuries, too short to represent orbital climate cycles, but consistent with recovery times from atmospheric loading by cosmic debris. As researchers continue analyzing geological archives with increasingly sophisticated techniques, they may discover that Earth's history includes more cosmic encounters than previously recognized. The signature of 3I/ATLAs and its debris trail might already be accumulating in contemporary sediments, creating a marker that future geologists could use to identify this period as a time when interstellar visitors began arriving with increasing frequency. The geological memory stored in rock layers, ice cores, and marine sediments represents humanity's longest-term archive of planetary environmental changes. These records demonstrate that Earth has survived numerous cosmic catastrophes, but also reveal that such events can trigger changes lasting millions of years. Understanding these patterns provides essential context for evaluating the potential consequences of future interstellar swarm encounters. Each layer tells a story of survival and recovery, but also of permanent change. The world that emerged from the Chicxulub impact was fundamentally different from the one that existed before, with new dominant life forms and altered climate patterns. Similarly, a major interstellar debris encounter might create a geological boundary that future scientists would recognize as the moment when Earth's trajectory through cosmic history took a new direction. The geological memory whispers warnings about the power of cosmic events to reshape planetary environments, while also demonstrating the remarkable resilience of Earth's interlinked systems. Both lessons remain relevant as we face an uncertain future in which interstellar visitors like 3I/ATLAS might herald changes as profound as any preserved in the ancient rock record. In the infrared sensitive detectors of the James Webb Space Telescope, 3I/ATLAs appears as a constellation of bright emission lines against the cold darkness of space. Each wavelength of light corresponds to a specific molecule vibrating in the comet's expanding coma, revealing chemical compositions that speak of formation conditions in an alien stellar system. Stephanie Millam adjusts the spectrometer settings, preparing to decode messages written in the language of atoms and molecules. The spectrum that emerges tells a story unlike any seen before in solar system comets. Prominent carbon dioxide lines dominate where water vapor signatures typically appear strongest. Carbonyl sulfide peaks indicate chemical processes unfamiliar from terrestrial or solar system experience. Most intriguingly, complex organic emission lines suggest molecular structures that could only have formed under specific temperature and pressure conditions around another star. Every molecule is a fossil, Millam explains, studying the data streaming from the Space Telescope. It preserves information about the environment where it formed billions of years ago. These molecules are telling us about chemical conditions that existed in a stellar system we'll never visit, around a star we may never identify. The molecular inventory of 3I/ATLAs reveals chemistry that challenges assumptions about comet formation. Solar system comets typically contain water ice, carbon monoxide, methane, and simple organic compounds in ratios that reflect formation temperatures in our own solar nebula. The unusual abundance patterns in 3I/ATLAs suggest formation in a markedly different chemical environment. Carbon dioxide ice, which makes up an estimated 40% of 3I/ATLAs's volatile inventory, normally forms only in the coldest regions of stellar systems, beyond the orbit of Neptune in our solar system. The prominence of CO2 over water vapor indicates that 3I/A Tellus originated in the outer reaches of its birth system, where carbon dioxide could condense while water remained largely in vapor form. Dr. Geronimo Villanueva of NASA's Goddard Space Flight Center leads the team analyzing molecular detections from 3I/ATLA. His research reveals isotopic ratios that provide additional clues about the comet's origin. The carbon-12 to carbon-13 ratio is slightly different from solar system values, he notes. This tells us about the nuclear processing history of the star where these materials formed. Stellar nucleosynthesis, the fusion processes that create heavy elements in stellar cores, produces different isotopic signatures depending on the star's mass, age, and metallicity. The carbon isotope ratios in 3I/ATLA suggest formation around a star with different nuclear processing history than our Sun, possibly a more massive star that produced enhanced carbon-13 through different fusion pathways. The sulfur-bearing compounds detected in 3I/ATLAS present particular mysteries. Carbonyl sulfide, hydrogen sulfide, and sulfur dioxide all appear in the comet's spectrum, but in combinations rarely seen in solar system objects. These sulfur compounds typically form through high-temperature chemical reactions, yet they coexist with carbon dioxide ice that requires extremely cold formation conditions. This apparent contradiction suggests a complex formation history involving multiple distinct environments. 3I/ATLAS might have formed initially in the cold outer regions of its stellar system, then subsequently processed through warmer inner regions where sulfur chemistry could occur, before being ejected into interstellar space by gravitational perturbations. Laboratory experiments conducted by Dr. Murthy Gudipati at NASA's Jet Propulsion Laboratory examine how different chemical environments affect molecular formation in cosmic ices. His team creates simulated interstellar conditions in vacuum chambers, exposing various ice mixtures to radiation and temperature cycles that mimic conditions during interstellar travel. We're trying to understand whether the chemistry we see in 3I/ATLAS represents its original formation conditions or changes that occurred during millions of years in interstellar space. Gudipati explains, some molecules are quite stable, preserving their original state. Others can be altered by cosmic ray bombardment or interaction with the interstellar medium. The organic compounds detected in 3I/ATLAS provide the most intriguing chemical signatures. Spectroscopic analysis reveals emission lines consistent with complex carbon-bearing molecules, including aldehydes, alcohols, and possibly even amino acid precursors. These organic species represent building blocks for more complex biochemistry, raising questions about the potential for life-related chemistry in the comet's parent system. The detection of these organic compounds required extraordinary sensitivity from the James Webb Space Telescope. Most of the targeted molecules exist in concentrations measured in parts per million within the comet's coma, making them extremely difficult to distinguish from background noise and contamination from Earth's atmosphere. Dr. Emmanuel Lelouch of the Paris Observatory has spent decades developing techniques for detecting trace molecules in cometary spectra. His expertise proved crucial for confirming the organic signatures in 3I/ATLAS data. We're looking for molecular fingerprints hidden within thousands of other spectral features, he explains. It's like trying to identify a whisper in a crowded stadium. The discovery process involves comparing observed spectra with extensive databases of laboratory measurements for individual molecules. Each compound produces unique absorption and emission patterns at specific infrared wavelengths, Confirming a molecular detection requires matching multiple spectral lines simultaneously while ruling out potential interference from other compounds. The isotopic analysis of detected molecules provides additional layers of information about formation processes and evolutionary history. Different isotopes of the same element behave almost identically in chemical reactions, but can be distinguished by their slightly different masses, which affect vibrational frequencies in molecular bonds. Deuterium. Heavy hydrogen with an additional neutron serves as a particularly sensitive tracer of formation conditions. The deuterium to hydrogen ratio in water molecules reflects the temperature at which the ice originally condensed. Higher ratios indicate formation at lower temperatures, while lower ratios suggest warmer formation environments. The deuterium content of 3I/ATALS water vapor matches values typical of Oort cloud comets, suggesting formation in similarly cold conditions, despite the comet's interstellar origin. This similarity indicates that the physical processes governing comet formation operate consistently across different stellar systems, even when the detailed chemistry varies. Nitrogen isotope ratios provide complementary information about stellar nucleosynthesis and chemical processing. The nitrogen-14 to nitrogen-15 ratio in 3I/ATLS differs subtly but measurably from solar system values, consistent with formation around a star with different nuclear burning history than our Sun. These isotopic signatures serve as cosmic archaeological evidence, preserving information about stellar and planetary formation processes that occurred billions of years ago in a distant part of the galaxy. Each isotope ratio represents a measurement of conditions that existed when 3I/ATLS's parent star was actively forming heavy elements through nuclear fusion. The molecular complexity observed in 3I/ATLS raises fundamental questions about the universality of organic chemistry. If complex molecules can form and survive in the interstellar environment, then the chemical precursors for life might be more widely distributed throughout the galaxy than previously assumed. Terrestrial biochemistry relies on a relatively small number of key molecular families: amino acids for proteins, nucleotides for genetic material, lipids for cell membranes, and carbohydrates for energy storage and structural support. The organic compounds detected in 3I/ATLAS include potential precursors for several of these molecular families. Dr. Scott Sanford of NASA's Ames Research Center studies how cosmic ice processing can create complex organic molecules. His laboratory simulations demonstrate that radiation bombardment of simple ice mixtures can produce amino acids, nucleotide bases, and other biologically relevant compounds through purely chemical pathways. We're seeing that the universe is quite good at organic chemistry, Sanford notes. Simple starting materials plus energy input can create remarkably complex molecular structures, including many that are essential for life as we know it. The implications extend beyond astrobiology to questions about the chemical inventory available for planet formation around other stars. If interstellar objects like 3I/ATALs routinely carry complex organic molecules, then young planetary systems may inherit substantial quantities of preformed organic materials that could accelerate the development of life. The chemical processing that occurs during interstellar travel adds another dimension to this organic inventory. Cosmic ray bombardment gradually alters molecular structures over millions of years, potentially creating chemical diversity that exceeds what formed originally in the comet's birth system. Studies of organic compounds in meteorites reveal similar chemical complexity. suggesting that organic molecule formation represents a universal process operating throughout the galaxy. The Murchison meteorite, which fell in Australia in 1969, contains over 80 different amino acids, far more variety than the 20 amino acids used by terrestrial life. This chemical diversity raises intriguing possibilities for alternative biochemistries that might develop using different molecular foundations than terrestrial life. 3I/ATLAs might carry organic compounds that could serve as building blocks for entirely different approaches to self-replicating chemistry and metabolic processes. The temporal stability of complex molecules during interstellar travel represents a key constraint on their potential biological relevance. Laboratory studies suggest that most organic compounds remain stable in interstellar conditions for millions of years, but gradual degradation by cosmic radiation eventually breaks down the most complex structures. The molecular lifetime depends on the specific compound structure and the radiation environment encountered during interstellar travel. Simple molecules like methane and ammonia can survive essentially indefinitely, while complex proteins and nucleic acids would be destroyed within thousands of years. The detection of apparently fresh organic compounds in 3I/ATLAs suggests either that these molecules formed recently during the comet's approach to our Sun, or that they were exceptionally well preserved during interstellar travel. Both possibilities have implications for understanding organic chemistry in cosmic environments. Thermal processing, as 3I/ATLAs approached the Sun, could have triggered chemical reactions between simpler precursor molecules, creating the complex organic signatures observed by telescopes. This scenario would imply that interstellar comets might serve as chemical laboratories, synthesizing new molecular combinations as they interact with stellar radiation fields. Alternatively, if the organic compounds survived from the comet's original formation, they represent chemical snapshots of conditions in an alien stellar system billions of years ago. This preservation scenario suggests that interstellar objects could serve as repositories of ancient chemistry, carrying molecular libraries from across the galaxy. The chemical analysis of 3I/ATLAs provides humanity's first detailed look at materials formed in another stellar system. Each detected molecule represents a sample of alien chemistry, offering insights into physical and chemical processes operating under conditions that may never be duplicated in our solar system. As the comet continues its journey away from the Sun, these molecular signatures will gradually fade as sublimation depletes the volatile materials that create the observable coma, but the chemical information already gathered will continue generating scientific insights for years to come. Each molecule a messenger from another world that traveled for millions of years to deliver its chemical news. The chemistry of invasion reveals that interstellar visitors carry more than just rock and ice. They transport molecular libraries that encode information about stellar evolution, planet formation, and organic chemistry operating under conditions far removed from terrestrial experience. In this sense, 3I/ATLAs represents not just a cosmic visitor, but a chemical ambassador bearing news of how nature operates in distant corners of the galaxy. The discovery of 3I/ATLAs marked the third confirmed interstellar object detected in just 8 years. Oumuamua arrived in 2017, followed by 2I/Borisov in 2019, and now this carbon dioxide-rich wanderer from beyond the solar system. To statisticians studying cosmic encounter rates, this clustering raises an intriguing question. Are we witnessing a natural statistical fluctuation, or does this pattern suggest something more systematic about interstellar object arrivals? Dr. Robert Werrick sits before banks of computer monitors at the University of Hawaii, analyzing detection efficiency curves for various sky survey programs. As the discoverer of Oumuamua, He understands both the capabilities and limitations of current observation systems. Finding 3 interstellar objects in less than a decade was completely unexpected, he admits. Our models predicted we might see one every few years, not multiple objects arriving in apparent clusters. Statistical analysis of rare events requires careful consideration of detection biases and observational selection effects. The apparent clustering of interstellar visitors coincides precisely with the period when automated sky surveys achieved sufficient sensitivity to detect such objects. This temporal correlation might simply reflect improved detection capabilities rather than genuine changes in arrival rates. However, the orbital characteristics of detected interstellar objects reveal patterns that challenge purely random explanations. All 3 confirmed visitors approached from directions roughly aligned with the solar system's motion through the galaxy. This directional bias might indicate that Earth encounters preferentially those interstellar objects whose trajectories intersect our orbital path, creating artificial clustering in the observed sample. Dr. Abraham Loeb of Harvard University has proposed more exotic explanations for the apparent clustering. His analysis of Oumuamour's unusual properties, including its elongated shape and anomalous acceleration away from the Sun, led him to suggest possible artificial origins. The probability of detecting 3 natural interstellar objects in such a short period raises questions about whether we're seeing truly random encounters, he argues. Population synthesis models, developed by researchers at the European Southern Observatory, attempt to predict natural interstellar object encounter rates based on stellar formation and evolution processes throughout the galaxy. These models account for mechanisms that eject planetary material from stellar systems, planetary system instabilities, stellar encounters, and supernova explosions that can blast material across interstellar distances. The calculations suggest that typical stellar systems eject substantial quantities of debris during their evolution. Young systems undergo chaotic orbital rearrangements as planets migrate to stable configurations, ejecting countless smaller bodies. Mature systems experience periodic disruptions when passing stars perturb the outer comet clouds, sending material on interstellar trajectories. Dr. Sean Raymond of the University of Bordeaux has modelled these ejection processes for different types of stellar systems. His simulations indicate that systems with multiple giant planets, particularly those in eccentric orbits, prove most efficient at ejecting smaller bodies. The galaxy should be filled with debris from billions of years of planetary system evolution, he notes. The question is whether our local region contains typical densities or unusual concentrations. The galactic environment around our solar system provides crucial context for interpreting interstellar object encounters. We currently travel through the local bubble, a region of low-density interstellar medium created by ancient supernova explosions. This relatively empty region might contain fewer interstellar objects than typical galactic neighborhoods, making recent detections potentially unrepresentative of long-term encounter rates. Alternatively, our current galactic location might expose us to debris streams from specific stellar formation regions. The Scorpius-Centaurus Association, a nearby group of young massive stars, has undergone substantial stellar evolution over the past 10 million years. Supernovae within this region could have injected unusual quantities of ejected planetary material into our local interstellar environment. The velocity distributions of detected interstellar objects provide additional clues about their origins. Oumuamou 3I/ATLAs both showed velocities consistent with the local standard of rest, the average motion of stars in our galactic neighborhood. This suggests local origins rather than high-speed ejection from distant stellar systems or exotic acceleration mechanisms. However, 2I/Borisov displayed significantly higher velocity relative to the local standard of rest, indicating possible origin from a different galactic region or more energetic ejection process. This velocity diversity suggests that detected objects represent samples from different source populations rather than a single homogeneous group. Dr. Matthew Holman of the Harvard-Smithsonian Center for Astrophysics studies orbital dynamics that might explain apparent clustering patterns. His research suggests that gravitational focusing by the Sun and outer planets could create preferential detection zones where interstellar objects become more visible to Earth-based telescopes. Objects approaching from certain directions get gravitationally accelerated and deflected in ways that make them brighter and easier to detect, Holman explains. This could create artificial clustering in the observed population, even if the underlying arrival distribution is completely random. The finite observation window for interstellar objects adds another layer to statistical interpretation. These visitors typically remain detectable for only months before fading below telescope sensitivity limits. Objects that arrive during periods when major telescopes are offline for maintenance, or when weather conditions prevent observations, might be missed entirely. Survey telescope scheduling and observing strategies also introduce systematic biases. Most automated surveys focus on regions of sky away from the Milky Way's galactic plane to avoid confusion with background stars. Interstellar objects approaching from galactic plane directions might be systematically underdetected, creating apparent directional clustering in the observed sample. The small number statistics of interstellar object detections make definitive conclusions about arrival patterns premature. With only 3 confirmed detections, any apparent patterns might disappear as larger samples become available. Paulson statistics for rare events predict substantial scatter in detection intervals, making short-term clustering statistically expected even for perfectly random arrival processes. Future survey capabilities will dramatically improve interstellar object detection rates and statistical reliability. The Vera Rubin Observatory will survey the entire southern sky every few nights, potentially detecting hundreds of interstellar visitors annually. This improved detection rate will quickly resolve questions about whether recent discoveries represent statistical anomalies or genuine patterns. The Legacy Survey of Space and Time, conducted by the Rubin Observatory, will also enable retrospective detection of interstellar objects in archival data. Computer algorithms capable of identifying moving objects in time series observations might reveal previously unrecognized interstellar visitors in decades of existing sky survey data. Dr. Mario Jurek of the University of Washington leads development of detection algorithms optimized for transient and moving objects in large survey datasets. His team estimates that archival analysis might increase the known population of interstellar objects by factors of 10 or more, providing much larger statistical samples for pattern analysis. The possibility of directed interstellar traffic remains a topic of active debate. While most researchers favor natural explanations for observed clustering patterns, the unusual properties of some detected objects continue to generate alternative hypotheses. Oumuamwa's elongated shape and non-gravitational acceleration remain difficult to explain through conventional comet or asteroid models. Theoretical studies of interstellar probe designs suggest that artificial objects optimized for interstellar travel might indeed display properties similar to those observed in Oumuamwa. However, the lack of detectable radio emissions or other technological signatures makes artificial origins highly speculative rather than scientifically supported. The search for artificial signals from interstellar objects has become a priority for SETI research programs. The Breakthrough Listen project includes protocols for monitoring newly discovered interstellar visitors for possible technological signatures. So far, these searches have detected no evidence of artificial origin, but improved sensitivity might reveal subtle signals missed by initial observations. Gravitational wave astronomy provides a new tool for understanding galactic-scale processes that might affect interstellar object populations. The merger of stellar mass black holes or neutron stars can eject substantial quantities of material at high velocities. Recent gravitational wave detections suggest that such merger events occur more frequently than previously estimated. Dr. Kenta Hotakezaka of the University of Tokyo has modeled how neutron star mergers might contribute to interstellar debris populations. His calculations suggest that these energetic events could account for some fraction of high-velocity interstellar objects, particularly those with unusual compositions reflecting nuclear processing in extreme stellar environments. The chemical diversity observed in interstellar objects supports multiple source populations rather than a single dominant ejection mechanism. Balmamo's apparently rocky composition differs markedly from the icy comet-like properties of 2I/Borisov and 3I/ATLS. This diversity suggests sampling from different types of planetary systems or different ejection processes. Climate cycles and orbital variations might also influence interstellar object encounter rates over longer timescales. As the solar system orbits the galactic center, it passes through spiral arm regions with different stellar densities and interstellar medium properties. These variations could create long-term cycles in interstellar debris encounter rates spanning millions of years. Geological records of cosmic impact events might preserve evidence of past interstellar object encounters, but distinguishing interstellar impacts from solar system events remains extremely challenging. Isotopic signatures provide the most promising avenue for identifying extraterrestrial material, but such analysis requires well-preserved samples from known impact sites. The apparent clustering of recent interstellar object discoveries has transformed them from curiosities into urgent research priorities. Whether this clustering represents statistical coincidence, observational bias, or genuine patterns in galactic debris populations will become clearer as detection rates improve and larger samples become available. Each new discovery adds critical data points for understanding the frequency, origins, and properties of interstellar visitors. The probability paradox, posed by recent clustering, might soon resolve into a clearer picture of humanity's place in a galaxy filled with wandering debris from billions of evolving stellar systems. In the climate modeling laboratories at the National Center for Atmospheric Research, supercomputers work continuously to simulate Earth's complex environmental systems. Atmospheric circulation patterns, ocean currents, carbon cycles, and biological processes interlink through countless feedback loops that maintain the delicate balance supporting life. But Dr. Clara Rodriguez faces an unprecedented challenge modeling what happens when multiple cosmic impacts simultaneously disrupt these interconnected systems. The concept begins with a simple question that leads to disturbing complexities. Earth's ecosystems evolved over billions of years to function as integrated networks, where disturbances in one component propagate through the entire system. A single large asteroid impact can trigger global climate changes lasting centuries. What might happen if dozens of smaller impacts occurred simultaneously across multiple continents? Traditional climate models excel at simulating gradual changes, rising carbon dioxide concentrations, slowly warming temperatures, or shifting precipitation patterns that develop over decades. Sudden, widespread disruption from cosmic impacts poses challenges that stretch these models beyond their design parameters. The mathematics of cascading system failures requires new approaches to computational environmental science. Dr. Alan Robock of Rutgers University pioneered climate modeling studies of nuclear winter scenarios, examining how massive fires and atmospheric dust loading could trigger global cooling. His research provides a foundation for understanding sudden atmospheric disruption, but cosmic swarm impacts introduce variables not considered in nuclear winter models. Nuclear explosions are concentrated events with predictable energy release patterns. Robock explains. Cosmic impacts scattered across the globe introduce spatial and temporal complexity that makes the modeling much more difficult. Each impact site responds differently depending on local geology, ecosystem types, and atmospheric conditions. The energy budget calculations provide the starting point for impact swarm modeling. Individual objects small enough to avoid creating permanent craters might still release energy equivalent to nuclear weapons when they explode in the atmosphere. The Chelyabinsk meteor of 2013, measuring only 17 meters across, released energy comparable to 30 Hiroshima bombs. A debris stream containing hundreds of such objects could deposit energy equivalent to thousands of nuclear explosions across the planet within a matter of hours or days. Unlike nuclear weapons, which explode at ground level, most cosmic impacts release their energy at altitudes between 20 and 50 kilometers, affecting atmospheric circulation patterns in ways that surface explosions do not. The atmospheric loading effects of simultaneous impacts could prove more significant than individual energy releases. Each atmospheric explosion injects dust, vapor, and chemical compounds into the stratosphere, where they can persist for months or years. A swarm encounter might load the atmosphere with particles beyond its capacity for natural clearing processes. Dr. Michael Mills of the National Center for Atmospheric Research develops atmospheric chemistry models that account for how cosmic debris affects ozone depletion, radiative balance, and chemical reaction pathways. His simulations reveal that certain impact compositions could create unexpected atmospheric chemistry changes. The sulfur-rich composition we see in some interstellar objects could produce massive quantities of sulfuric acid aerosols. Mills notes, these particles not only block sunlight, but also catalyze ozone destruction reactions. The combination of cooling and ozone loss could create atmospheric conditions unlike anything in Earth's recorded history. Marine ecosystem modeling reveals particularly concerning vulnerabilities to atmospheric disruption. Ocean food webs depend on microscopic phytoplankton that require sunlight for photosynthesis. These organisms form the base of virtually all marine food chains, supporting everything from fish populations to whale communities. Atmospheric particle loading that reduces surface sunlight by even 20 or 30% could trigger collapse of primary productivity in ocean ecosystems. Historical examples include the 1991 eruption of Mount Pinatubo, which reduced global temperatures by 0.5 degrees Celsius and measurably affected marine productivity for several years. Dr. Michael Follows of MIT studies marine ecosystem responses to environmental perturbations using coupled climate biology models. His research shows how changes in ocean temperature, acidity, and light availability propagate through marine food webs, with effects that persist long after initial atmospheric disturbances clear. Marine ecosystems have very long recovery times, Follows observes. Phytoplankton populations can crash within months, but rebuilding complex food webs takes decades. If atmospheric loading persists for several years, we could see essentially complete collapse of marine fisheries worldwide. Terrestrial ecosystems face different but equally serious vulnerabilities during extended atmospheric disruption. Land plants can survive temporary light reduction by drawing on stored energy reserves, but prolonged photosynthesis reduction leads to widespread forest die-offs and grassland ecosystem collapse. The timing of impact swarms relative to seasonal cycles could prove critical for ecosystem survival. Events occurring during growing seasons would have more severe effects on plant communities than those occurring during winter months, when many plants are naturally dormant. However, impacts during critical reproductive periods could affect population recovery capabilities for years. Dr. William Andreg of the University of Utah models forest ecosystem responses to environmental stress using data from drought, fire, and disease outbreaks. His research reveals that forest systems exhibit threshold behaviors where gradual stress accumulates until reaching tipping points that trigger sudden, widespread tree mortality. Forest ecosystems are surprisingly fragile once you exceed certain stress thresholds. Andreg explains, a cosmic impact swarm could push multiple forest regions simultaneously past their survival limits, creating continent-scale die-offs that would take centuries to recover from. Agricultural systems present immediate human survival implications for impact swarm scenarios. Modern agriculture depends on predictable weather patterns, stable temperatures, and consistent growing seasons. Atmospheric disruption that alters precipitation patterns or reduces growing season length could trigger global food shortages within a single year. The vulnerability of agricultural systems varies dramatically by geographic region and crop type. Tropical agriculture tends to be more resilient to temperature changes, but highly vulnerable to precipitation disruption. Temperate region agriculture can tolerate some temperature reduction, but requires specific seasonal timing for successful harvests. Dr. Andy Challinor of the University of Leeds leads research on climate change impacts on global food security using coupled climate crop models. His team has examined how sudden climate perturbations might affect agricultural yields across different scenarios and geographic regions. The global food system operates with remarkably little buffer capacity. Challinor notes, we typically maintain grain reserves sufficient for only a few months of global consumption. Any major disruption to agricultural productivity could quickly lead to widespread famine, particularly in regions that depend on food imports. Pollination network disruption represents a subtle but potentially catastrophic ecosystem vulnerability. Many plant species depend on specific pollinator insects for reproduction, creating complex networks of interdependence that maintain ecosystem stability. Atmospheric chemical changes from cosmic impacts could disrupt these relationships in ways that cascade through entire ecosystems. Recent research on pollinator decline provides alarming precedents for how quickly these networks can collapse. Bee populations have experienced dramatic declines in response to pesticide use, disease outbreaks, and habitat loss. Similar stresses from atmospheric contamination could trigger even more severe pollination network failures. Dr. Claire Kremin of the University of British Columbia studies pollination network resilience and ecosystem service provision. Her research reveals that pollination networks contain critical nodes, keystone species whose loss can trigger cascading failures throughout the system. Pollination networks are like ecological house of cards, Kremin explains. Remove a few key species and the whole structure can collapse rapidly. Atmospheric chemical changes from cosmic impacts might simultaneously stress multiple pollinator species, creating network failures that would be almost impossible to reverse. Freshwater ecosystem modeling reveals additional vulnerabilities to impact swarm scenarios. Lakes and rivers provide critical water resources and support distinct biological communities that respond differently to environmental perturbations than marine or terrestrial ecosystems. Acid rain from atmospheric sulfur compounds could rapidly acidify freshwater systems, causing widespread fish kills and ecosystem collapse. Historical examples from industrial pollution demonstrate how quickly acidification can eliminate entire fish populations from lakes and streams. The interconnectedness of different ecosystem types amplifies the consequences of simultaneous disruption. Terrestrial ecosystems depend on freshwater systems for water resources, while marine ecosystems receive nutrient inputs from terrestrial runoff. Simultaneous damage to multiple ecosystem types could prevent the cross-system recovery processes that normally help damaged regions recover. Dr. Monica Turner of the University of Wisconsin studies landscape-scale ecosystem dynamics and recovery processes following major disturbances. Her research on forest fires, floods, and other natural disasters reveals how ecosystem recovery depends on connectivity with undamaged reference areas. Ecosystems recover through seed sources, animal recolonization, and nutrient flows from surrounding areas, Turner explains. If disturbances are widespread enough to eliminate these recovery mechanisms, damaged ecosystems might shift into entirely different states that persist for centuries or millennia. Social system modeling reveals how ecosystem collapse would interact with human civilization in complex feedback loops. Human responses to environmental stress, including resource competition, migration, and conflict, could further accelerate ecosystem degradation through unsustainable resource extraction and habitat destruction. The Syrian drought of 2007 to 2010 provides a recent example of how environmental stress can trigger social disruption that amplifies ecological damage. Prolonged drought led to agricultural failure, rural to urban migration, social unrest, and eventually civil war that continues to affect regional stability. Dr. Kyle Davis of the University of Delaware studies coupled human environmental systems and their responses to climate stress. His research reveals how environmental degradation and social disruption create reinforcing feedback loops that can lead to societal collapse. Environmental stress doesn't occur in isolation. Davis notes, it triggers human responses that often make environmental problems worse. A cosmic impact swarm could create environmental stress beyond anything human societies have previously experienced, potentially triggering responses that accelerate ecosystem collapse. Economic modeling of ecosystem collapse scenarios reveals costs that exceed current global GDP by substantial margins. Ecosystem services, including climate regulation, water purification, pollination, and marine productivity, provide value estimated at over $100 trillion annually. Widespread ecosystem collapse could eliminate most of these services simultaneously. The insurance industry has begun developing catastrophe models for extreme climate events, but cosmic impact swarms fall outside the range of scenarios considered insurable. The potential for simultaneous global ecosystem disruption exceeds the financial capacity of any institution to provide meaningful compensation or recovery assistance. Recovery time modeling suggests that ecosystem restoration following major swarm impacts could require centuries to millennia. The Chicxulub impact 66 million years ago triggered ecosystem changes that persisted for millions of years, with completely new ecological communities eventually emerging to replace those that were destroyed. Modern ecosystems might prove less resilient than ancient systems due to habitat fragmentation, pollution stress, and climate change effects that have already pushed many systems close to their survival limits. Ecosystems that might have recovered from cosmic impacts under pristine conditions could fail to survive when additional stresses are considered. The cascade modeling reveals that ecosystem collapse represents potentially the most severe consequence of interstellar debris swarm encounters. While atmospheric disruption might persist for years and technological damage could be repaired within decades, ecosystem recovery operates on timescales that exceed human civilization's planning horizons. Understanding these vulnerabilities provides essential context for evaluating cosmic threat priorities and developing mitigation strategies. The interconnectedness that makes Earth's ecosystems so productive and stable also makes them vulnerable to simultaneous disruption from sources they never evolved to handle. In this sense, ecosystem collapse modeling reveals not just environmental vulnerabilities, but fundamental constraints on planetary resilience in an unpredictable cosmic environment. 540 million years ago, in the shallow seas of what would become the Burgess Shale, an extraordinary diversification of life was taking place. The Cambrian explosion marked the relatively sudden appearance of complex multicellular organisms with hard shells, articulated appendages, and sophisticated sensory systems. What triggered this unprecedented burst of evolutionary innovation remains one of paleontology's greatest mysteries, but some researchers suspect that cosmic events played a crucial role. Life has survived everything the universe has thrown at Earth, Irwin observes. Asteroid impacts, volcanic catastrophes, ice ages, and cosmic radiation bursts. Each challenge eliminated some species while creating opportunities for others to diversify and adapt. The history of life is essentially a record of survival and recovery from existential threats. Dr. Douglas Irwin of the Smithsonian Institution examines fossilized trilobites under a powerful microscope, studying the intricate compound eyes that allowed these ancient arthropods to navigate their marine environment. The evolutionary sophistication visible in these 500 million year old fossils represents solutions to survival challenges that Earth's organisms developed in response to changing environmental conditions. The late Devonian extinction involved multiple pulses of environmental stress spanning several million years. Ocean anoxia, widespread depletion of dissolved oxygen, eliminated many marine species. However, the crisis also drove the evolution of air-breathing adaptations in fish, leading eventually to the colonization of land by vertebrates. The deep time perspective reveals patterns of resilience that operate across geological timescales far longer than human experience. Earth has endured at least 5 major mass extinction events during the past 500 million years, each eliminating 50 to 90% of existing species. Yet life not only survived these catastrophes, but often emerged more diverse and complex than before. The Endordovian extinction, approximately 445 million years ago, resulted from global cooling that locked much of Earth's water in polar ice caps. Marine ecosystems collapsed as sea levels dropped, and ocean chemistry changed dramatically. Yet the recovery period saw the evolution of early fish and the colonization of terrestrial environments by plants and arthropods. Dr. Andrew Knoll of Harvard University studies how environmental stress drives evolutionary innovation. His research reveals that many of life's most important adaptations emerge during recovery periods following mass extinction events. Catastrophes eliminate dominant species and create ecological opportunities, he explains. The survivors radiate into vacant niches, often developing entirely new approaches to survival. The end Permian extinction, known as the Great Dying, represents the most severe crisis in Earth's biological history. Approximately 250 million years ago, massive volcanic eruptions in Siberia triggered global warming, ocean acidification, and widespread hydrogen sulfide poisoning, over 90% of marine species and 70% of terrestrial vertebrate species disappeared. Yet even this near sterilization event failed to eliminate life entirely. Small populations survived in refugia, isolated regions where conditions remained tolerable. These survivors became the ancestors of entirely new evolutionary radiations, including the rise of dinosaurs and eventually mammals. The recovery mechanisms that enabled survival through past cosmic catastrophes provide insights relevant to potential interstellar swarm encounters. Life's resilient strategies include genetic diversity maintenance, reproductive flexibility, metabolic versatility, and geographic distribution patterns that ensure some populations survive even widespread environmental disruption. Genetic diversity serves as life's insurance policy against environmental uncertainty. Populations with higher genetic variation contain individuals with different physiological tolerances and adaptive capabilities. When environmental conditions change rapidly, these genetic differences determine which individuals survive to reproduce and pass their traits to subsequent generations. Dr. Peter Ward of the University of Washington studies extinction and recovery patterns across multiple mass extinction events. His research identifies common survival strategies that characterize species likely to persist through environmental catastrophes. Generalist species with broad environmental tolerances consistently outsurvive specialists during mass extinctions, he notes. Geographic distribution also matters. Species with wide ranges are more likely to have populations that survive regional catastrophes. The cheetah population bottleneck provides a modern example of how reduced genetic diversity affects survival prospects. Cheetah populations underwent severe reduction during the Pleistocene ice ages, leaving modern cheetahs with remarkably low genetic variation. This genetic uniformity makes the species vulnerable to diseases and environmental changes that might not affect more genetically diverse populations. Conversely, species like rats and cockroaches maintain high genetic diversity and broad environmental tolerances that enable survival in diverse conditions. These characteristics explain why such species thrive in human-modified environments, while more specialized species decline. Reproductive strategies also influence survival prospects during environmental catastrophes. Species with rapid reproduction rates can quickly recover from population crashes, while long-lived species with slow reproduction require longer recovery times. However, long-lived species often possess greater individual tolerance for environmental stress. Extremophile organisms reveal the outer limits of life's environmental tolerances. These organisms thrive in conditions previously thought incompatible with life: boiling hot springs, highly acidic environments, intense radiation fields, and crushing deep ocean pressures. Their existence demonstrates that life can adapt to almost any stable environmental condition. Metabolic versatility provides another survival advantage during environmental stress. Organisms capable of utilizing multiple energy sources or tolerating extreme conditions maintain greater flexibility when primary resources become unavailable. Many bacteria exemplify this strategy, switching between different metabolic pathways as environmental conditions change. The albatross exemplifies life history trade-offs that affect extinction vulnerability. These seabirds live for decades and reproduce slowly, making population recovery difficult following major mortality events. However, their long lifespans allow individuals to survive temporary environmental disruptions that might eliminate shorter-lived species. In a secure facility beneath the Norwegian mountains, seeds from across the globe rest in frozen storage at -18 degrees Celsius. The Svalbard Global Seed Vault, often called the Doomsday Vault, represents humanity's attempt to preserve agricultural diversity against an uncertain future. As Dr. Marie Hager surveys the latest deposits from international gene banks, she reflects on how this seemingly modest underground chamber might serve as civilization's lifeline following cosmic catastrophes. We built this vault to protect against regional disasters, wars, climate change, natural disasters, Hager explains, her breath visible in the frigid storage chamber. But the design specifications actually make it suitable for much more extreme scenarios. The permafrost and thick rock overburden would protect these seeds even if the surface world faced major disruption. The concept of preparing for cosmic catastrophes extends far beyond seed preservation to encompass every aspect of technological civilization and biological survival. As the frequency of interstellar object detections increases, researchers across multiple disciplines are beginning to consider what comprehensive preparation might entail. Space-based early warning systems represent the first line of defense against cosmic threats. The proposed Near-Earth Object Surveyor mission would operate from the L1 Lagrange point, positioned between Earth and the Sun, to provide continuous monitoring of potentially threatening objects. From this vantage point, the spacecraft could detect incoming interstellar visitors months or years before Earth-based telescopes. Dr. Amy Mainzer of the University of Arizona leads the NEO Surveyor science team, developing detection algorithms optimized for discovering fast-moving objects against complex stellar backgrounds. Early detection is absolutely critical, she emphasizes. Every additional day of warning time multiplies our options for response, whether that's deflection attempts or preparation for impact effects. The technical challenges of space-based detection include distinguishing genuine threats from the millions of catalogued asteroids, managing data processing for continuous all-sky surveys, and maintaining reliable communications with Earth across interplanetary distances. However, these obstacles appear surmountable with current space technology. Complementary ground-based facilities could provide detailed characterization of detected threats. The extremely large telescope, currently under construction in Chile, will possess unprecedented capabilities for spectroscopic analysis of small, distant objects. Combined with space-based detection, these facilities could provide comprehensive threat assessment within days of initial discovery. Deflection technology development requires sustained investment in advanced propulsion systems capable of reaching threatening objects within months rather than years. Nuclear thermal propulsion represents the most promising near-term solution, offering specific impulses twice that of chemical rockets while maintaining reasonable complexity and development costs. Dr. Dante Loretta of the University of Arizona, principal investigator for the successful OSIRIS-REx asteroid sample return mission, advocates for developing standardized deflection spacecraft maintained in ready-to-launch status. We need planetary defense systems that can respond to threats detected with short warning times, he argues. This means having spacecraft already built and tested, waiting for deployment. The Stored Interceptor concept envisions multiple nuclear-powered spacecraft positioned at strategic locations throughout the solar system. These vehicles would remain in standby mode for years or decades, undergoing periodic maintenance and testing to ensure readiness for rapid deployment against detected threats. Economic analysis suggests that maintaining such a defense fleet would cost roughly $50 billion annually, substantial but comparable to current military expenditures of major nations. The insurance value against low probability but catastrophic cosmic impacts might justify this investment from a risk management perspective. Underground shelter systems provide protection against atmospheric effects from cosmic impacts or debris swarms. Existing underground facilities, including subway systems, mining infrastructure, and military bunkers, could serve as emergency shelters during atmospheric disruption events lasting months or years. The Swiss civil defense system provides a model for comprehensive underground protection. Switzerland maintains shelter space for its entire population, with facilities designed to provide life support during extended isolation periods. Similar systems could protect populations during nuclear winter scenarios caused by cosmic impacts. Dr. Martin Hellman of Stanford University, a veteran of nuclear policy analysis, studies civil defense approaches applicable to cosmic threats. The techniques developed for nuclear war survival translate directly to cosmic impact scenarios. He notes, underground shelters, food storage, air filtration, and communication systems provide protection against both nuclear weapons and atmospheric disruption from space. Food security systems require fundamental restructuring to survive extended agricultural disruption. Current global food production operates with minimal reserves, maintaining grain stocks sufficient for only a few months of consumption. Cosmic impacts that disrupt agriculture for years would quickly exhaust available food supplies. Vertical farming technologies offer potential solutions for food production during extended periods of reduced sunlight. These systems use LED lighting and hydroponic growing methods to produce crops in controlled environments independent of external climate conditions. While currently expensive, vertical farming could provide essential food security during cosmic catastrophe recovery periods. The Netherlands leads global development of controlled environment agriculture, with greenhouse systems that produce exceptional yields per unit area while maintaining independence from external climate conditions. Scaling such systems globally could provide significant insurance against agricultural disruption. Dr. Dixon Despommier of Columbia University pioneered vertical farming concepts as solutions for urban food security. His research suggests that vertical farms located in underground facilities could continue operating during atmospheric disruption events, providing fresh food when conventional agriculture fails. Genetic diversity preservation extends beyond the Svalbard seed vault to comprehensive biological sampling and storage programs. The frozen zoo concept, pioneered by conservation biologists, maintains genetic materials from endangered species in liquid nitrogen storage systems that could preserve biological diversity through catastrophic events. Advanced reproductive technologies, including in vitro fertilization, embryo transfer, and genetic engineering techniques, could enable species restoration even from minimal surviving genetic material. These technologies provide insurance against biodiversity loss that exceeds natural recovery capabilities. Communication system redundancy becomes critical for maintaining coordination during extended crisis periods. Current telecommunications depend heavily on satellite systems vulnerable to space weather and electromagnetic pulse effects. Hardened communication networks using underground fiber optic cables and low-frequency radio systems could maintain connectivity during cosmic crisis events. Amateur radio networks provide decentralized communication capabilities that remain functional when commercial systems fail. The global amateur radio community maintains emergency communication protocols specifically designed for disaster response scenarios. Dr. David Geary of the University of New Mexico studies electromagnetic pulse effects on communication systems and develops hardening techniques for critical infrastructure. Commercial communication systems are optimized for efficiency rather than resilience, he explains. Building truly robust communication networks requires accepting higher costs in exchange for guaranteed functionality during extreme events. Medical system preparation involves stockpiling pharmaceuticals, medical equipment, and supplies needed for treating injuries and illnesses during extended isolation periods. Cosmic impact scenarios could disrupt pharmaceutical supply chains for years, making advanced preparation essential for maintaining public health. The Strategic National Stockpile, maintained by the United States, provides a model for medical emergency preparation. This system maintains inventories of antibiotics, vaccines, medical equipment, and other supplies distributed across secure storage facilities throughout the country. Educational system preservation requires developing comprehensive archives of human knowledge in formats that remain accessible during infrastructure disruption. Digital storage systems provide enormous capacity but depend on complex technological infrastructure that might be damaged by electromagnetic effects or power system failures. The Internet Archive's mission to preserve digital information demonstrates the scale of effort required for comprehensive knowledge preservation. Their systems maintain copies of billions of web pages, books, movies, and other cultural artifacts in multiple redundant storage facilities. Dr. Brewster Cahaly, founder of the Internet Archive, advocates for distributed preservation systems that maintain copies of essential information across multiple geographic locations and storage media. We need to ensure that human knowledge survives whatever challenges the future might bring, he emphasizes. Energy system resilience requires developing power generation and distribution systems capable of operating during extended disruption periods. Renewable energy systems with local storage capabilities could provide essential electricity when centralized power grids fail due to electromagnetic effects or infrastructure damage. Microreactor nuclear power systems offer another approach to distributed energy security. These small modular reactors could provide reliable power for essential facilities during extended grid outages while remaining simple enough to operate with minimal technical support. Water system security involves developing treatment and distribution capabilities that function independently of centralized infrastructure. Personal water purification systems, local groundwater resources, and distributed treatment facilities could maintain water security when municipal systems fail. International cooperation frameworks need development to coordinate response efforts across national boundaries. Cosmic threats affect the entire planet simultaneously, requiring unprecedented levels of international coordination for effective preparation and response. The Outer Space Treaty provides a legal foundation for international space cooperation, but additional agreements specific to planetary defense scenarios would enhance coordination capabilities. The United Nations Office for Outer Space Affairs has begun developing planetary defense guidelines, but these efforts remain in early stages. Dr. Sergio Machado Rezende, former director of the UN Office for Outer Space Affairs, emphasizes the importance of international coordination for cosmic threat response. Cosmic impacts don't respect national boundaries, he notes. Effective preparation requires global cooperation on detection, deflection, and disaster response. Psychological preparation involves developing social systems and cultural practices that enhance community resilience during extended crisis periods. Historical studies of disaster response reveal that social cohesion and mutual support networks significantly affect survival rates during catastrophic events. The COVID pandemic provided recent experience with global crisis response, revealing both strengths and weaknesses in current social systems. Public health measures, economic support systems, and international cooperation mechanisms demonstrated remarkable adaptability while also showing clear limitations. Dr. Susan Clayton of the College of Worcester studies psychological responses to environmental threats and develops interventions to enhance individual and community resilience. People cope better with crises when they feel some sense of control and community connection, she explains. Preparation efforts should include psychological as well as physical components. Research and development priorities should focus on technologies most relevant to cosmic threat scenarios. Advanced propulsion systems, underground life support technologies, radiation protection methods, and closed-loop ecological systems. Sustained investment in these areas could dramatically improve survival prospects. NASA's research into closed-loop life support systems for Mars missions directly applies to underground shelter scenarios. These systems recycle air, water, and waste products to minimize external resource requirements during extended isolation periods. The integration of preparation efforts across multiple domains — detection, deflection, shelter, food security, communication, medical care, energy, water, international cooperation, and psychological support — requires comprehensive planning that exceeds any single organization's capabilities. Current planetary defense efforts focus primarily on detection and deflection, but comprehensive preparation requires equal attention to survival and recovery capabilities. The infrastructure needed to survive extended cosmic catastrophes overlaps significantly with preparation for other low probability but high consequence threats. Climate change adaptation, pandemic preparedness, and nuclear war survival planning all involve similar challenges: maintaining essential services during extended disruption, preserving genetic and cultural diversity, and coordinating international response efforts. Investment in comprehensive resilience systems provides insurance against multiple threat categories. The cost of comprehensive cosmic catastrophe preparation likely exceeds $1 trillion globally, substantial but manageable when spread across decades and multiple nations. This investment would create infrastructure beneficial for multiple applications beyond cosmic threat scenarios. As interstellar visitors, like 3I/Atlas, arrive with increasing frequency, the urgency of such preparation efforts grows accordingly. While the probability of any specific cosmic catastrophe remains low, the cumulative risk over decades or centuries becomes significant enough to justify major preparation investments. The unthinkable has become thinkable, transforming cosmic catastrophe preparation from science fiction speculation to serious policy consideration. Whether humanity chooses to invest in comprehensive cosmic resilience will determine how well civilization survives its first encounter with a truly threatening visitor from beyond the solar system. Each component of preparation, from seed vaults to space-based detectors, represents humanity's attempt to maintain some measure of control in an unpredictable cosmic environment. Together, these efforts could provide the foundation for surviving challenges that have eliminated countless species throughout Earth's history, ensuring that human civilization endures whatever surprises the universe might deliver.